Hi, good morning. Can you hear me?
Good morning, Elizabeth. I can hear you.
Okay, do you want to try to test the videos and cameras, etc.?
We can do that. We've got an online speaker who'd like to test the videos and the cameras and stuff. Is that okay? In the Zoom? In the Zoom. First speaker in the Zoom. Yep. We're just asking the tech guys right now.
Ah, okay.
Photo.
Okay.
She is speaking?
Yes, I'm speaking. Can you hear me? Blah, blah, blah.
Hello. Good morning, ma'am.
Good morning.
Can you hear us?
Yes, I'm here. Can you hear me?
Two.
Qu'est-ce qui fait que l'icône est en zoom out?
Hello.
Hello, can you hear me?
Can you hear me?
Try to share screen.
Yeah. Okay.
Okay.
Yes. Yeah. Can you speak something?
Yes, I'm trying to share my screen. Could you see my screen, full screen?
Okay.
Okay. Can I stop sharing?
Yeah.
Okay, great. No, I'm not able. Okay, yes. Yeah. Thank you. It seems
All right.
that
Thank you.
it's perfect. Thank you very much.
I think you're speaking from there, but they kind of want you to be sitting there. We also just wanted to confirm how we say your Okay, I'll do my best. Good morning, everybody. We're a few minutes away from starting our first talk of the day. This is Spectroscopy 3, observations of small bodies in the solar system in the context of large surveys, upcoming large surveys. And we just wanted to do a quick introduction. I'm Amanda Citrus. Yeah, thank you all very much for participating.
Papa,
The topic is a pretty big umbrella, so we've got everything coming up from
Papa, Zoom na yo, get them ready.
So we've got NEO characterizations, we've got instrumentation, we've got working with large data sets, and the first round is actually fast follow-ups using global networks of telescopes. So we've got a big range of stuff all associated with solar system bodies and upcoming surveys. We are going to have a few invited talks, as you'll see in the program. Those are 20-minute slots, so there will be 17 minutes for the talk and then 3 minutes for questions. The other talks are 10-minute talks, which means you have 7 minutes for the talk and then 3 minutes for questions. The speakers are going to give you a 2-minute warning. And of course, because we're doing this online and in person, we're going to have to keep on track. So you got to keep to our time slots. So if you go over the time, somebody's going to gently usher you off the stage, or we'll cut you off if you're speaking virtually. Any other logistics? We had thought that the speakers were supposed to sit up front, but we're such a small group that I think you're probably more comfortable just staying where you are. And do I need this?
I think online.
Online. Sorry if you can't hear me online. That we're such a small group that the speakers are going to take questions immediately after their talk. So I don't think you need to kind of be uncomfortable sitting up here in the front, if that's okay with everyone. Are you happy to stay where you are? Okay, great. And then at exactly 10:30, we'll be kicking off with the first talk. So thank you very much. To introduce the talks. So we have 3 minutes.
Okay, can you hear me? I think so. Okay, first of all, many thanks to the organizers for having invited me to present this talk and to discuss with you the challenging issue of the fast reaction follow-up, in particular of newly discovered near-Earth objects. As we know, small NEOs become bright enough to be physically characterized from Earth only for very limited time spans, coinciding with close approaches with the Earth, whereupon they could become unobservable for years or even for decades. Therefore, it is
need to stop you. I'm so sorry. We didn't start your talk here. We were waiting for 10:30 to start, and we've just put you up on the screen.
Okay, yes,
So-
I made a mistake because I was not sure to be that you introduced me. Okay, thank you.
Thank you so much for being eager to go, and you just got to practice the first part one more time. In 1.5 minutes, I will introduce you, and we'll give you the go.
Okay, great. Sorry.
Thank you so much. So when she starts, you're going to start the timer, is that right? So you can see it? Perfect. All right, we are introducing our first speaker for today. This is an invited talk by Elisabetta Dotto, Fast Reaction Follow-Up and Global Networks of Telescopes.
Okay, thank you very much. Okay. So first of all, many thanks to the organizers for having invited me to present this talk and to discuss with you the challenging issue of the fast reaction follow-up, in particular of newly discovered NEOs. As we know, small NEOs become bright enough to be physically characterized from Earth only for very limited time spans, coinciding with close approaches with the Earth, whereupon they could become unobservable for years or even for decades. Therefore, it is fundamental for us linking up NEO discovery, astrometric follow-up, and physical characterization in order to improve our knowledge of the physical nature of these bodies, as well as to properly address the NEO impact monitoring and mitigation. This can only be achieved through a coordinated approach, ensuring a quick reaction time, guaranteed access to medium to large aperture telescopes, and the development of efficient methods for dynamical and physical characterization. And in this topic, we had a great experience with the project NEOROX, funded by the European Union in the framework of the Horizon 2020 program and carried out between 2020 and 2023. The NEOROX project was focused on near-Earth objects. And here we have all the ambitions of this project, and we had the creation of a network of large aperture telescopes. We worked to improve the neophysical properties modeling and simulations and the orbit determination process. We established the neophysical property data center in the Space Science Data Center at the Italian Space Agency. And we fostered international cooperation for follow-up, and we addressed the imminent impact on monitoring. After our experience with NEOROX, we were able to fix this roadmap for physical characterization and the needed actions to increase our knowledge on the physical properties, which are ranking the neophysical properties in order of importance and purpose, as an example, mitigation, exploration, exploitation, etc. Keeping a list of known properties of known NEOs as a function of their rank, mapping the sites where relevant information can be extracted and or inserted, and support scientists to cooperate in improving the physical characterization of any given NEO. We created a matrix of observables, reporting the different observational techniques performed in close coordination among the different partners and groups within the NEOMIR project, in order to increase the possibility of a rapid determination of high priority physical properties. Here on the right, we have the observation accuracy trade-off, where different colors corresponds to different degrees of achievable accuracy, and darker shades correspond to better accuracy. Here we have the physical properties prioritization, which is fundamental for properly planning the activities and maximize the exploitation of the obtained data. The essential physical properties needed to model in the occurrence of and the consequence of an impact are listed against the technique needed for determining them. So the importance for planetary defense is highlighted using different colors. The property follows the rainbow sequence. Red means highest and violet means lowest, while observing modeling decreasing tone implies decreasing accuracy. We also considered the observation from space, taking into account the contribution given by onboard instrumentation, mission design, spacecraft characteristics, and the overall cost of some ongoing space observatories able to observe near-Earth objects. Also considering that, as demonstrated by LICHA-CUBE, which witnessed the impact of DART on Dimorphos, small spacecraft and CubeSats represents a promising alternative in terms of shorter lead time and higher cost.
Sorry for just a second.
Yes.
We've lost sound. Pause for a second. Sort that out. Oh. Now you're back. Sorry about that. Go ahead.
Oh, I'm sorry. Okay. We took also into account that the experience we gained with LICHA-CUBE, which witnessed the impact of DART on Dimorphos, and take into account this experience, we say that small spacecraft and CubeSats represent a promising alternative in terms of shorter lead time and higher cost effectiveness. And therefore, spacecrafts and CubeSat are very appealing for extending into space the elements of a rapid response system for the imminent impactors. So these are the items we finalized as fundamental in building a fruitful international cooperation for neophysical characterization and for rapid response systems. As we already seen, establishing priorities on physical characterization for planetary defense, and in this respect, space mission contribute in increasing the information on the physical properties of these bodies. Working and focusing on data dissemination, data policy, and standardization, linking ground-based observations of newly discovered objects, and performing a rapid response experiment, and as the next steps, prototyping this experience also for civil protection. And this is the work breakdown structure of the rapid response experiment that was performed within ROCS, with different working packages and responsibilities. So the working package which worked on orbit characterization implemented a rapid response system scenario based on robotic telescopes through developing procedures and software. And the package working on physical observations carried out the physical characterization upon short notice through project observational network. Then we analyzed the outcome and they produced the data, and we produced the final recommendation. Here we have the activity change of the NEOROX rapid response experiment, which and this part was performed as an automatized procedure. The chain included monitoring the priority list, checking the visibility from the Minor Planet Center site, producing ASCII files providing coordinates, angular speed, and also maximum exposure times and number of frames required, defining the setting, namely polling intervals and number of output, minor planets code, minimum elevation, maximum magnitude, scale, pixel resolution, sensitivity, and so on. And here we have the first test we performed on January 2022. Unfortunately, our telescope network for physical follow-up was not able to observe the whole list of targets selected by the automatized telescopes because of the weather conditions. And once the weather conditions were good again, the targets were no longer observable due to their faintness. So after this first test, we learned several lessons. We discussed the follow-up procedure and obtained the results, and we focused our attention on all these issues to optimize further experiments. As an example, we decided to start our second experiment before the new moon to have more useful nights. We focused our attention on the approaching targets so that their magnitude would increase during the nights. We focused our attention to not to high declination, not to allow us to observe these targets even from the southern telescopes. We selected not to faint, not to low solar elongation targets, and so on. And we decided to implement two different strategies: a blind experiments on known targets and a rapid response campaign focused to newly discovered objects. And in the night between the 3rd and the 4th of April 2022, we carried out highly automatized observations of a sample of newly discovered NEOs. The information was rapidly disseminated within the NEOROX consortium in order to perform quick follow-up observations of the target's physical properties. And among the observed targets, Asteroids 2022 GC1 was the subject, as an example, of a Director Discretionary Time request to the Telescopio Nazionale Galileo in Canary Islands. And the observations were activated in the following nights. And this is the results we obtained. It is noteworthy that both astrometric and physical follow-up observations were completed in a matter of days, which is a very promising figure for facing the imminent impactor problem. And this is another target, 2021 VM25. And also in this case, its physical properties were retrieved in less than 3 weeks. So here we have the scenario of, I would say, normal observations, standard observations. We have NEO surveys for discovery, individual telescopes to follow up, which contribute to the Minor Planet Center database and to the NEO confirmation page list. And we have a lot of individual databases. So we can say that every observer has his own or her own database. And here we have the new scenario after the NEOROX proof of concept. We automatized the link to NEO confirmation page via NEOScan. We partially automatized the link with observers, and we put all the results in a common physical properties database that was at the Space Science Data Center of the Italian Space Agency. So in conclusion, we had fast response times of on the order of days, weeks. We have seen that being able to timely carry out the physical characterization of an imminent factor is a key feature for future developing a rapid response system for civil protection purpose. We have demonstrated that using the European existing assets, it is possible to set up an integrated imminent impact or rapid response system encompassing both dynamical and physical characterization. And here we have the recommendation for future. These recommendations were elaborated at the end of the NEOROX project on the basis of our experience. The first one is about fostering and securing follow-up observations devoted to physical characterization through either managing dedicated assets or easing access to telescope time. And for that, it's very important to have a strong institutional empowerment to enlarge the number of available and dedicated telescopes and to have access to large aperture telescopes even upon short notice. This is very, very, very important. The second recommendation is about promoting and adopting standardized data management and data policy practice within the initiatives devoted worldwide to neophysical and dynamical characterization. And finally, the third recommendation about the imminent impactor threat, with the goal of realizing a fast, rapid response system for civil protection. And to this purpose, it's very important to prioritize the physical properties according to their importance for planetary defense in order to define a different level of engagement and data policy. And finally, by investigating secure and efficient communication protocols between astrometric and physical follow-up in order to improve automated processes. And this is my last slide. Thank you very much for your attention.
Thank you, Elisabetta. We have time for questions. Any question for Elisabetta? I can start with one. Elisabetta, hi, it's Federica Spoto from the Center for Astrophysics. I just wondering if you could say a few more words about the case of imminent impactors when we discover something that, is a few hours before impacting and how that would rescale according to the model you were presenting for especially physical properties. How difficult would it be? Thank you.
It's very difficult. It's very difficult because we need dedicated telescopes. It's fundamental for us to have rapid access to the telescopes, but even to have dedicated telescopes to the physical properties. Otherwise, we risk to lose these objects without any possibility to have their characterization, unfortunately. We have seen that we need a time span of days, weeks for characterize them. So it's very, very difficult without dedicated telescopes to carry out observations in a few hours.
Thank you. Other questions?
Hello, Elisabetta, Daniel Estoffer from Paris Observatory. I had a question on very first slides you showed about the priority list with the rainbow colors. And I was just, my question is this for the imminent impactor or in general? Because the mass for me would be in the top list physical parameter to know even before the size or diameter or
Yes, actually.
Of the mass. So I was just surprised about having the mass at the end.
No, you're perfectly right. The problem is that we focused this activity on Tunguska-like object. So in this experiment, in this prioritization scheme, we have in some way, we already know the mass. So for this reason is at the end, because it's, I can say, second level determination. We already know that these targets are in the Tunguska scale dimension, but in general, you are right. I've forgotten to say that. Thank you very much, Danielle.
Okay, thank you. We have one more question. Sorry.
Thank you. Gersbauer, University of Maryland. I just wanted to ask Elisabetta if you make use of other NEO prioritization programs like NEO Fixer, and are you open to incorporating also other ranking software like might be implemented for NEO Surveyor?
Sorry, can you repeat the question?
Yes, when you're with the follow-up programs, are you incorporating also other possible sources for ranking like NEO Fixer for it's a Catalina Sky Survey product, or NEO Surveyor Fixer, which is TBD, but I think is in the works?
We started from the Minor Planet Center list and the Minor Planet Center confirmation page list. So, but I mean, this is just the first experiments, but it's very important to prototype such an experience, opening all the list of available targets for sure.
All right, I'm sorry about that. We're having some sound difficulties here. I apologize. We are on to the next speaker who is in person, so hopefully this will all go well, except apparently she doesn't have a pointer, so bear with us, please.
Thank you very much.
Of telescopes in Southeastern Europe to large asteroid surveys, and Todorovic will be presenting.
Okay, thank you. First of all, I would like to thank you all, to the organizers, and I hope that we will all bring very special memories from this place and from the meeting. So I will speak about the telescopes in Southeast Europe. So in case that someone is not from the field, a small reminder that currently there are about 1.2 million known asteroids. Of the formation process in the solar system, and to identify potentially dangerous asteroids. Another small reminder is the location of Southeast Europe. So Southeast Europe is not a strict geographical term. There are variations on the internet, but according to the Europlanet Society, these 9 countries are placed there. But only the first 5 countries, I don't have a pointer, I cannot show, but only the first 5 countries are members of the International Astronomical Union, having astronomical institutions. Here's the light pollution map of Europe, where we see that the region is actually not so polluted as these most developed parts of Europe, but still it's not dark enough. So the biggest telescopes in the region, okay, thank you. So the biggest telescopes in this region are in the 1 meter class telescopes. So there are 5 observatories having these telescopes. Here I will mention them. In Serbia there is one here, 1.4 meters, named after Milankovic. Then in Bulgaria there are 2 at the Rožen Observatory, 2 telescopes with 2 and 1.5 meters, and in Greece 3 telescopes, and the largest is 2.3 meters. It's the first point here. So this is the location of where they are placed, and they are all used for asteroid observations. But as we probably all know, that the time on such telescopes is very limited, and for asteroid observations we need a lot of observational time. So here is where the small telescopes are basically more convenient for asteroid observations. So here is another map showing all telescopes in the region with an observational code and used for asteroid observation. So here is the distribution by countries. The largest number is in Romania, 13. And so besides the observatories in scientific institutions, there are also the backyard observatories, public observatories, and observatories incorporated in school. And this map is interactive, so if you are interested to see more, it can be found on this link. I can give you the link later. So we are interested, what is the contribution of these telescopes to large asteroid surveys? So I have to admit that I didn't know much about this, so I don't know these people in person, so I did one by one research for each of these telescopes, and here's what I found. So focusing on, there are other projects as well, but here we speak about asteroids. So besides the regular photometric observations that are sent to the Minor Planet Center, there are 9 projects related to asteroid surveys, and most of them are related to near-Earth asteroids, so you can look at them better. I don't have time to go through all of them. I will mention only these 2 projects. So the first one is the so-called ancient asteroid projects, which started about 4 years ago in Greece, with the idea to find the oldest asteroids in the solar system. So this is the most recent publication that was submitted recently to astronomy and astrophysics, and the authors verified that Altor and Zeta are the oldest, among the oldest families in the solar system, and this was done by investigating the sense of rotation, and one of the parameters was in investigating the sense of rotation, and here's the main result of the paper, where we see the spin states for 84 asteroids, 42 for each Altor and Zeta family. These asteroids are marked in color depending on the direction where they are rotating, and for these 84 asteroids, the authors obtained 366 new light curves, which involved more than 1,000 hours of observation from 9 observatories. And then, in addition to this data, more than 800 light curves were used, and sparse data from sky surveys and space observatories in addition were used. So this huge amount of data was used only for 84 asteroids. So we have more than 1 million and have to discover even more. So this is actually one example that shows, the need for massive observational programs and the need for mutual collaboration. So one telescope, no matter how good it cannot be enough. And the other example is our Serbian in-kind contribution to LSST follow-up photometric observations. This program is named SERSAG S2. It will be done on the Milankovic telescope. Here it is. Here's the telescope. My colleague will tell you more about this telescope and in one of the following sessions. But the idea is that this LSST will make millions of alerts, and many telescopes around the world will characterize and supplement these discoveries, and Milankovic is one of those telescopes. So again, we focus on asteroids and near-Earth asteroids, and using the solar system model by Gravetol 2011 and the object in field package, we estimated that LSST will discover for about 42,000 new near-Earth asteroids, and this is the number of observation of these asteroids, where we see that most asteroids will be observed about 10 times. But there are also asteroids that will be observed several hundreds of times. So among these 42,000, 28,000 will be observable from our Milankovic telescope in idealized condition. And here we compare the magnitudes of the asteroids from LSST and the 28,000 from the Milankovitch telescope. We cut the magnitude at 22. So these are the apparent magnitudes, and here we can compare the absolute magnitudes of these two data sets. And I believe I was done. I was okay in time.
Perfect. Thank you. Thank you. Is it working? All right. Is it working? No. Yeah? Okay, perfect. Any questions? If you have any questions online, also please put it in the chat. We'll read them. Yeah?
Hi. So I was wondering, what's the plan for detecting the asteroids in the LSST? Will you go directly to the data releases from the LSST?
I don't work on LSST, so Željko is here. Željko Ivesić. Okay, we have a perfect man for this piece.
Sorry.
Ruben Observatory will be issuing alerts within 60 seconds of closing shutter in Chile. And then those alerts that will include everything we measured in different images will be sent to brokers, and you can get them from there. Or if you want to wait 24 hours, they will be loaded to MPC. And if you go after alerts, all the known asteroids will be flagged by our pipelines. So you can simply subscribe to that alert stream, and you are good to go within a few minutes of discovering that object.
Any more questions? Yeah, down there. Sorry.
Yeah, so I was wondering how do you plan on selecting from all of the LSST alerts which asteroids to follow up with the Serbian telescope?
Well, this is a good question. Probably it will depend on the current situation. I mean, we neglected the cloudy nights. We have a lot of cloudy nights and humidity in winter. In summer, we have good nights, but short. So it will depend. Or maybe we will make some small software to do that.
Thank you so much. Let's thank the speaker again, and we'll move on to the next one.
Thank you. Krugli, photometric monitoring of near-Earth asteroids.
Hello, everybody. Thank you, organizer, for giving me to take this conference and for financial support and any assistance. And our work, I don't see my presentation, sorry. Our work is concerned to the observation and investigation of the near-Earth asteroids.
Okay, sorry, just a second there. We're not seeing your presentation. If you could share. We can see you, just not the presentation.
You can? Can I take...
Could you please share your screen on your side?
Yes, okay. Yeah, it's right there. Sorry. Yes. Okay.
Just give it a sec. It looks like it's coming. Yes.
Yes.
Go into slide, show view.
Okay. Sorry, some difficulties. It's
Control L.
Okay. Oh yeah. Yes.
Okay. Thank you.
The work is collective. Many people on this slide, you can see that it's my collaborators from different observatories, different countries. And our work with investigation of physical properties of near asteroids. Near-US asteroids started long time ago. Some history of stage of our monitoring of near-US on this slide. 1995, we started in collaboration with Planetary Science Institute in Berlin with our colleagues from there. And this is work was concerned to the follow-up astrometry and photometry of the newly discovered NEAs. And again, next stage of our including is the process of investigation of the near-Earth asteroids. It's the 1997 when we started to search and to investigate of binary asteroids by photometry with Piotr Pravec from the Czech Republic. And next stage was 2004 when we started to work with many people in Europe to determine the Europe effect, to observe the asteroids for which we we obtained the Europe values. And next stage was 2007, investigating of small clusters and asteroid pair with people from Czech Republic, Kralitsky David, Piotr Pravec, and others. And now we worked with this telescope with people from these observatories, from Bulgaria, from Georgia, from Uzbekistan, and from US. They have good telescopes at the Chile STIA Observatory. And below you can see the 70 centimeter telescope. It's our home telescope, very close to our city, Kharkiv city, nearly 70 kilometers from Kharkiv, Chuguyev Observatory. We did our observation many years, long time, and now it's stopped. It's a pity, but it's stopped because this problem. We have 2 years ago, February 24, Russia started the big war against Ukraine, and this territory we are located, the Chuguyev Observatory, was occupied, and in half a year later, this was the occupied Ukrainian army, and you can see on the slides that we saw after returning to this observatory fully destroyed and completely plundered, and any observation we can do now, we have some struggle to repair this observatory, our telescope there, sorry. But we are alive and we continue our investigation of near-Earth asteroids. It's the slide showed the object between the near-Earth asteroids that we investigate by photometry and polarimetry. It's a study newly discovered near-Earth asteroids and especially potentially hazardous near-Earth. We also investigate binary asteroids and try to search new binaries and investigate Europe effect for asteroids. And also between our targets of observations, there is a radar targets and targets of space missions. And this is the short example of some of our work with small near-Earth asteroids with diameter smaller than 300 meters. And you can see on left two pictures the light curve of asteroids with very short rotation period. First one has 6 minutes period rotation, and another one it's the 11 minutes asteroids. You can see that this asteroids very fast rotates, but have LIGO have the different amplitude. It's a different shape of these asteroids. One of them is elongated, another one close to the sphere. So the fast rotation has asteroids has different shapes. And another two slides on the right, the slides of the slides, it's the asteroids with also the small and have a more bigger period rotation. And you can see that these asteroids can rotate very fast and also slowly. And it's the results of our next year observation with different targets that we observed. You can see that big list for radar targets for small NEOs smaller than 300 meters diameters. And also we observed seven asteroids newly discovered and obtained at rotation periods, and observed good known binary asteroids for improving their parameters, and also observed three asteroids, namely Phaeton, Didymos, and also object of a future Hayabusa 2 extended mission object 2001 CC 21 asteroids. And on the right, you can see the picture of spin rotation of near-Earth asteroids. You can see that this asteroid rotates very fast and slowly, and it depends from its history, from his evolution. And the binary asteroids, near-Earth asteroids, marked by blue. And also you can see by red marked the objects that observed in our cooperation during last year. You can see that we observed different asteroids with different diameters and different rotation period. And very short time for presentation. And I can see that this is some summary of our job that we spent on the last year. And I again want to say thanks for organizer for my financial support. And all of you want to say the good, the take part on this beautiful conference. Thank you very much.
Thank you. Unfortunately, we don't have any time for questions, but if you have questions for the speakers, please ask them online. And now we move on to the next one.
Thank you.
The next speaker is Exploring Capabilities, Characterizing Solar System Objects with SAO Telescopes, and it's given by Erasmus.
Okay, good morning, everyone. Thank you for coming. As you heard, my name is Nick. I'm an astronomer at the South African Astronomical Observatory, or SAO for short. And I'll be presenting today on some of the facilities we have at our observatory, specifically that I've been using in the past few years for observing solar system objects. So if you're not familiar with our observatory, our headquarters are in Cape Town, but our observing site where our telescopes are located is roughly 450 kilometers northeast of Cape Town in a semi-desert region close to the town of Sutherland. And as you can see from this aerial shot, we have many telescopes there, ranging from a couple of centimeter in aperture to the big 10-meter SALT telescope at the back there. And these three dominant older-looking domes with the grey cladding, these are three telescopes that are fully owned and operated by the observatory. But you can see many, many other telescopes on site. These are hosted facilities, so these are facilities by international partners. But as hosts or the South African community does also have access to a certain small percentage of time on some of these telescopes. So I'll be focusing on the 3 that we fully own and operate for now. So the first 2 is our 74-inch and 40-inch. These are the oldest telescopes on site. The 74-inch can host one of 3 instruments, a spectrograph, a polarimeter, and a high-speed imager. I've mainly been using the high-speed imager for my observations. This imager is based on the frame transfer Andor camera, so it can do very fast frame rates. Duplicate system is available on the 40-inch, and currently both of them have, because of the large F ratio of these old telescopes, a fairly modest field of view, but good enough to do some observations. And we also have full filter sets in both the Sloan and Johnson Cousins. Just some examples of observations we've done using these 2 telescopes. This was by a previous master student of mine. She was doing multi-filter light curves of NEAs, doing rotation period determination, and also taxonomic types through the colors. And as you can see, the telescopes can also do non-sidereal tracking, which is obviously useful with a fairly small field of view. Just a quick mention, my co-chair Amanda can tell you all about this, but these Andor cameras, the shock systems were specifically designed to do very high frame rates. So if you're not cycling filters and sticking to one filter, you can observe these very short occultation events, which are usually a couple of seconds. These frame transfer cameras have almost 0 daytime. The next telescope is our new 1-meter telescope. This telescope is about 10 years old now, so it's not that new, I guess, but fully robotic. It also has the ability of 2 instruments on its 2 Naismith ports. The one that I've been using now extensively over the past few years of my students is this instrument called McCordy. It's a cousin of the Spratt instrument, so if you've ever used the Spratt on the Liverpool telescope, this is sort of a very similar instrument. I'm not going to go through all these specifications, but just briefly say that this instrument can do both low-resolution spectroscopy and imaging, and can switch between the 2 modes very quickly. In fact, the imaging mode is used for the auto-target acquisition. And so both this telescope and the instrument are fully robotic. And this is sort of running our flagship program at the moment. So because this telescope is fully robotic, it's one of the first telescopes that we've incorporated into our Intelligent Observatory initiative. So this is an initiative that the observatory has started to sort of modernize and upgrade our telescopes and roboticize those that can be roboticized, and also in some way network all the telescopes we have on the plateau. And the ultimate aim is to do, or one of the ultimate aims is to do better and more efficient rapid follow-up of target of opportunity type observations. And because we have an Atlas telescope on site, which is designed to discover near-Earth asteroids, but also discovers a lot of transients, we can really do this rapid follow-up because we can discover on site and even observe during the same night at the same site. And so this flagship program that we've been using or doing is done by my master student, Toby Kile. So I'm not going to talk too much about this because she has a talk on Thursday talking all about this program, but essentially we're doing rapid same-night follow-up of NEAs using this robotic telescope. Then we've also used this robotic telescope for ad hoc observing of other solar system objects. This is an example of an Iowan Capet we took part in, so 2023 DZ2. We also took this very famous observations of the dart impact of Didymos. So this was done with that Lesedi telescope in McCordy. I think this animation even features on the Wikipedia page. And again, we could do very fast time resolution light curves of this event. Then hosted facilities. This is KMTNet. It's a South Korean telescope that's mainly doing microlensing events, but we do get some time on this telescope that we can apply for. So a few years ago, it has a very large field of view. We did sort of a mini survey of main belt asteroids and sort of did a study of asteroid families doing taxonomic determination of each target we observed. IRS-F, it's a Japanese telescope. slightly different to other telescopes in the sense that it can do JHK imaging and also simultaneous imaging. So again, do multi-filter imaging. This was another IWIN campaign. I think this was 2012 TC4. And yes, I would like to conclude with that. So future plans, we want to incorporate more of our telescopes in this rapid follow-up program that we're running, specifically SALT, and specifically with LSST discovering fainter things. We really want to be using the full possibility of a 10-meter telescope to chase after fainter stuff. IRSF we've used in the past, but it's not incorporated in our follow-up program, so that's another possibility. There's also another new telescope that's been installed, Prime, another Japanese telescope that we would be able to get target of opportunity time on. Also incorporate that. And then one thing that I'm particularly interested in is the telescopes that I've just shown you have instruments that I haven't used for NEA follow-up in the past. For instance, I'm quite interested in doing polarimetry. So if anyone in the audience is familiar with that and wants to collaborate, please get in contact with me. And just in general, we are open to collaboration. So yeah, please get in contact with us if any of these facilities are attractive to you. Thank you.
Thank you. Any questions for Nick? I have one. Oh, sorry. Go ahead. Yeah, go first.
Yeah, oh, sorry, I should introduce myself. Colin Snodgrass, University of Edinburgh. I was wondering whether or not with your intelligent control, you'd be able to simultaneously use different telescopes. So could you use like the simultaneous visible imaging and the simultaneous JHK imaging on the same target at the same time?
Yeah, so as I said, the LSST telescope is the only telescope that's sort of plugged into that system at the moment, but we are planning to expand it to all the other telescopes. So that's exactly the idea, so to do more coherent and intelligent follow-up, so if a target comes in, there's some intelligence that determines, okay, we do spectroscopy with this telescope, photometry with that telescope, and ideally at the same time, right? Yeah, that's the idea.
Any more questions? Okay, I can ask mine. Are you planning to use the telescopes for NEA's occultations?
That's an interesting question. I did actually pose that question to Amanda because I don't know much about occultations, and
there are no more questions. Let's thank the speaker again.
All right. Following on that presentation about the South African telescopes, we have a talk on the spectroscopy of primitive asteroids with the Southern African Large Telescope, and it's being given by Michailova.
Good afternoon, everyone. Good morning. I hope you can see my
Just
screen.
1 second, Sophia. We don't have your sound yet. Sorry. Okay, try now, please.
Can you hear me? Is everything okay?
Thank you. Good.
Thank you. Thank you for the opportunity to give me a talk. And today I would like to tell you about our project about spectroscopy of primitive asteroids done with the Southern African Large Telescope. And yes, I'm Sofia. I'm a PhD student of Adam Mickiewicz University in Poland, and this topic is a part of my PhD thesis. So first I would like to explain why we decided to study these objects. Primitive asteroids are carbonaceous asteroids which have in their composition hydrated minerals. They have some unique features in their spectra, and for this project we decided to study so-called C-complex asteroids, which include C, B, F, and G taxonomical types. And you can see on the slide here on the plot, the most interesting for us feature is absorption in near ultraviolet range, which is, let's say, the main interesting thing which we would like to found in this spectras. Moreover, we would like to study the absorption of hydrated minerals and 0.7 micrometer bands. And these features, they were found some times ago, and on this slide you can see some small retrospective of studies of near ultraviolet range and variation in this range. And first, this variation was detected by Tholen in his famous work. Later, it was explained by presence of hydroxyl in composition of these asteroids, and correlation between absorption in near ultraviolet range and infrared band was found. Also, due to laboratory studies, was found a correlation with hydrated meteorites, and it's well enough to say that this region in spectra very interesting and can be used for founded hydrated minerals. So the goals of our projects is determination the absorption in near ultraviolet range, also the depth of 0.7 micrometer absorption band. Also, we would like to found a correlation between taxonomical type, between size of asteroid and heliocentric distance, and the absorption. Plus additional tasks is finding spectral solar analogs in this region. So for this, we begin our programs on 10-meter Sol telescope. It was started less than 1 year ago, from November. We already took time twice. 2 observational semesters were done, and we got, for both of them, we got priority 1, the highest priority time, for obtained 5 spectra of these carbonaceous primitive asteroids plus solar analogs. And also we got a P4 time with low priority for founding stars which can be candidates in solar analog stars. So our asteroids, the criteria of choosing these asteroids, they have to be a member of C-complex families. I mean, it have to be P, B, C, or G types. Or they have to be a member of family in which the main body has confirmed one of these taxonomical types. The brightness range up to 17 magnitudes, so it's well enough for 10 meter for study in near ultraviolet. And of course, they have to be visible in southern hemisphere. And additionally, in the same night, we got a spectra for confirmed solar analog stars. I mean, confirmed as solar analog in near ultraviolet region. And for new stars, which you would like to study, you can see on the screen the criteria, how we choose these targets. The definition of those targets have definition as a solar twin. So you can see again the criteria, plus we also check the color of the star, and of course it has to be visible in the southern hemisphere, and this project will be done for the first time for southern hemisphere. So our project is long-sleeve spectroscopy, low resolution. Observation are done in 2 modes, blue and red. And in total, we have a spectra for asteroids and for stars in the range between 0.32 to 0.9 micrometers. And for now, we already got 20 spectra. In particular, it's a spectra of 7 asteroids plus solar analog stars. And 3 spectra of new stars, which can be a candidate in solar analog. And I want to say that this project is first for us and first for SOLT. I mean, before it was not done spectroscopy for this range. And some troubles, we had some troubles about this. And as you can see, during our first semester, we got only 50% of time. But for now, we already finished our observation with 100, almost 100% time which was used. And here is the example of our spectrum which we got. And as you can see, it looks very well. You can see the absorption which we are looking for. For our observation, we will use a CANA package. It's a special package for determine all these features about what I'm talking. And unfortunately for this asteroid, we didn't found 0.7 micrometer band because this asteroid is B-type asteroid and it's not common for this type to see the depth of this band. And we would like to collect more observations because, as I said before, for now we got only 7 asteroids, spectra for 7 asteroids, but we applied for a next semester, and in collaboration with Nicholas Erasmus, we got twice more time. I hope we will get, because for now it's just submitted, and it means that we will have twice more targets for this semester. Also, we would like to continue our program for SOLT, like a long-term program for next years. Plus, we have some scientific plans, like we would like to found a correlation between absorption in near-ultraviolet and near-infrared, and also study influence of space weathering on spectral features for near-UV absorption. And we would like to include also laboratory studies, but it's just a perspective. And we are very grateful for our collaborators and for the SOLT team that they're not scary to try this program and the studies, the observations in near-ultraviolet range. And thank you for your attention, and please feel free to contact us via email or via Slack. Thank you.
Thank you. Any questions? We have time for a quick question. I'll ask a quick one. Are you planning to expand this analysis to other families, like other spectral types in the future?
No, we are not planning. We are planning to do it only for primitive asteroid, I mean C-complex, plus maybe Jupiter Trojans, but that's because these spectral features which we are studying, they're for now, they found only for these types. But for another one, no.
Thank you. Let's thank our speaker again.
Thank you. And next we have an in-person talk, Search and Study of the Near-Earth Orbit within Ground-Based Optical Telescopes at NRIAG Egypt, and it's going to be given by Mursi.
Hi everyone, my name is Ahmed Mursi from Egypt, National Research Institute of Astronomy and Geophysics. My presentation titled Search and Study of Near-Earth Orbit within Ground-Based Optical Telescope at NRIAG Egypt. This project funded from Egyptian Space Technology Center, STDF. Our project divided into two kinds of observation or two directions. First direction, space debris and satellite observation, and the other direction, near-Earth object. Yes, here we can show in the NRIAG facilities. We have some of telescopes at NRIAG. First telescope, 74-inch telescope. This for near-Earth object and asteroid observation. Other telescope, 36-centimeter telescope for space debris photometry. The third telescope, 1.2 meter telescope for both observation, asteroid and space debris with laser ranging. And the last telescope, small telescope for optical satellite tracking station for space debris and satellite observation with large field of view about 8 degree square. For observation, we make some international cooperation with other scientific from other countries, such as ISON, International Scientific Optical Network for asteroid and for space debris observation. As you see, we can see here Klet Observatory in Egypt belong to this international cooperation. This represents the elevation of space environment, both satellite and space debris, and both near-Earth asteroid discovery and by discovery and by large and size. Our direction in NRIAG in space debris observation, we may make a global survey for whole geo objects, tracking bright geo and MEO object, searching and follow up faint debris object. Our goals: maintenance of space debris database, support of daily updated list of orbits of this object, including conjunction assessment analysis, and observation surface under commercial request. We have two directions for observation. First, leapfrog tracking for star apparent as point for low Earth orbit, and the other tracking mode, continuous tracking with speed of space debris or asteroid or satellites. This apparent magnitude for our small telescope up to 16 magnitude, and this residual along track and other kind of our observation, asteroid. We can skip this. This is our strategy in large telescope, optical surveillance, astrometry, and photometry. We make some follow-up for object, and we confirming some object which detected by an cooperation observatory. This from our cooperation, we have cooperation with, as I talk with ISON, within this observatory, Tsumani 70 centimeter from Georgia, and from Mongolia, and from Chinese, and this object which observed by our telescope besides this we make the discovery for 5 objects, 2 comets and 3 near-Earth objects, and we have some observation for other asteroid for multicolor observations. And this example of our observation from 1.8 meter telescope. And this example of our results for some object with small telescope. We determined the rotation period about 2.4 hours. This according typically as published. Also, with a small telescope, we determined the period of which close approach Earth in last months. We determined this period this object is have non-regular rotation period, but we determined this rotation period from 40 to 58 minutes. Also in right side, this observation for 2024 NS object which close approach last 1 August, maybe from 3 days. Now we're working on processing observation with Poznan Observatory in Poland to determine the rotation period of this object. We expect this trembling asteroid because we have about two rotation periods. The first period about 2 hours, 2 hours, and the other period may be larger than this period. Also, we have determined some rotation period for other objects, as like this binary asteroid, primarily rotates with period about 2.4 hours, with light curve amplitude of 0.2 magnitude. Also, I mentioned we have about new discovery about 5 objects. First observation on 10 of January, last January, by Purple Mountain Observatory in China, and then they request us to confirm this object, and we confirmed this object on 15 of January. Also, we confirmed other object, the last object comets, possibility comets, we confirmed it as true comets, and there are other 2 objects. Beside observation of asteroid and space debris, we make some observation for stellar occlusion by asteroid. The last one we observed this occlusion of brightness star G. This transition object was in destination with this object maybe from 2 months ago. This my last slide, and thank you for the observation.
Thank you. Any questions? How do you prioritize your follow-up? Do you have a way of like choosing targets?
Yes, we have as a cooperation with Purple Mountain Observatory in China. Maybe request they have a large telescope, I think a 2-meter telescope for sky survey. Then they request us to confirm some of objects. Besides, we have some object from new confirmation IAU Binary Center.
Thank you. More questions? If not, let's thank the speaker again. Thank you.
Thank you very much. Luckily, the rest of the talks in the session are in person. So next up, we have near-Earth objects follow-up astrometry at Klet Observatory, 30 years of experience in Central Europe, and the talk is being given by Tia.
So my name is Jana Tichá, and I serve as the director of Klet Observatory, which deals with near-Earth object tracking more than 20 years. Klet Observatory is situated in central part of Europe, in the Czech Republic, near to the Austrian and German borders. At elevation more than 1,000 meters above sea level, in a rather dark site in the center of a natural protected area. We started with NEO astrometric follow-up in 1992 with using 0.57 centimeters telescope equipped with CCD. We got more than 20,000 near asteroids astrometric measurements, and to the most interesting objects belong asteroid 1996 JA1, which is up to now the largest body with so close approach to the Earth, and later smaller Earth impactor 2008 TC3, which was discovered at Piškeštěto by Christian Charnecký, and we were alerted both by NEOCP and by Marco Micheli from ESA, and my colleague Miloš got its observations just 12 minutes before its disintegration above the Northern Sea, south from the small Jan Mayen Island. Considering increasing number of near asteroids discovered and decreasing level of its brightness, we decided to build a new, larger and most effective telescope, which is now called Klet telescope, with diameter 1.06 meter, equipped with 2K to 2K CCD. It gives a larger field of view, 37 to 37 arc minutes, with computer-controlled equatorial mount. We got with this newer telescope more than 50,000 near asteroids astrometry measurements, and also discovered 3 NEOs at Klet. We used for this work continually upgraded Klet software package for the whole workflow. One of the recent things added to this package is work with Gaia EDR3 star catalog for astrometry. Here are some graphic presentation of our results. If you consider it with big differences between the years, then it depends mainly on weather conditions in Central Europe, where we on the borderline of Atlantic weather and continual type of weather, and it is more and more difficult in the recent years with weather. The big gap is in the years of large reworking of telescope mount, and the year with the highest number of observed both bodies and measured positions is year 2020. It is the COVID year, when we have very, very good weather in our country, fortunately. From interesting near-Earth asteroid object observed and measured by Klet telescope, I selected as an example small Earth impactor 2022 EB5, discovered at Piškeštěto, which was the 5th small Earth impactor observed before, not before hitting the Earth, but before disintegration above the Northern Sea. And my colleague Milos got the last astrometry of this object just 12 minutes before its disintegration. Moreover, to our NEO tracking work, we try to submit the public outreach of NEO research and asteroid hazard for students, for teachers, for educations, for media, and also for decision makers of our country. So it is last year visit of the President of the Czech Republic at Klet Observatory. As in conclusions, I would like to mention advantages of Klet Observatory, which are full observing time is dedicated to our team. We obtained long time NEO experiences at Klet Observatory since 1992. So we have experienced observers and measures. The observing time belonging to us give us possibility of quick changes of observing plan even during continuing night. And for rapid response follow-up astrometry, we are able to do almost real-time processing of targeted objects and data flow to the minor planet center. It is important to say that we working as ESA cooperating sensor since 2014. And for the future, we would like to go to find the objects using quading images and also offset tracking of near asteroids, and work in the field of rapid response follow-up for special objects. In future, we also think about the automatic of telescope from of it in the construction of the mount of the telescope. So we are ready to continue our cooperation in NEO tracking field, and thank for your attention.
Thank you. Sorry, we have no time for questions at this time, but yeah, feel free to talk to the speaker.
Our final talk of the session is evaluating the LSST's capability to detect interstellar objects that can be followed up with the Milankovitch telescope, and it's being given by Marcetta.
Okay, thank you very much. This talk will be more about simulations and less about actual observations. I'm Dusan Marcetta from Serbia, from Department of Astronomy. I mean both asteroids, so inactive objects, and also comets. And actually one of the major goals of our work is to estimate the ratio between comets and asteroids that LSST will discover. And another goal for this particular talk is to estimate roughly the fraction of objects that could be observed with our Milankovitch telescope, which is situated in Serbia, and which is already a part of Serbian in-kind contribution to the LSST. So, what have we done so far? We use this algorithm from 2023 to generate a large number of synthetic populations of interstellar space. So this algorithm allows you to generate easily different synthetic populations with user-defined characteristics such as number density, size frequency distribution, kinematics. And here is just another output for this algorithm. This is the distribution of incoming directions along the sky, where you can see that the majority of the objects come from the direction of the solar apex. And here is, in our previous work, we used objects in field algorithm. And here's just one nice output for our previous work, where you can see the sky paths of the discovered objects with LSST field of views at the time of the detection. But now we are using, for our current work, we are using this extremely powerful software package called SORCA, which allows simulation of LSST observations of the solar system objects. It is very fast and efficient and allows simulation of a large number of phenomena such as rotational light curves, cometary brightness, trailing losses, fading function, etc. It is really easy to use. It is still not officially released, so now we are using the current state of the software, which is available on GitHub. So we only have some preliminary results with the current state of the software, but we are setting all our simulations and preparing that once the software is released, we will rerun our simulations. So now about the simulations, since the interstellar population is very poorly, it is poorly constrained because we only have two discovered objects, so we don't know exactly how their orbits and other characteristics look like. So we generated a large number of different synthetic populations. We use different size frequency distributions. For now, we only used this simple power law with these 6 different slopes, but we will include others. And as I said, we simulated asteroids with for now 5 different albedo options, which you can see here, and also comets with 12 different brightness models, details of which can be found in this Cook et al. Paper from 2016. So in total for now it is like 30 asteroidal and 72 cometary populations, but we will include more. We expect to have at least 500 different synthetic populations of the interstellar objects. And as I said, one of the major outputs from our preliminary simulation is this plot here, where you can see the ratio of the number of the comets to the number of asteroids that LSST will discover, depending on the horizontal axis is size frequency distribution. It is cut off, I'm sorry. And these different colors present different brightness models that we assumed for the comets. And here you can see that this ratio should range from factor of few to few orders of magnitude in favor of comets, of course. And inverse, if we have, let's say, 1-to-1 ratio of discovered asteroids to comets, this figure would imply the ratio of their number densities in the interstellar space. So we have a lot of other outputs from our SORCA simulations. I'll, due to the limited time, I'll show you just some of them. This, for example, the distribution of the sizes of the objects, which switch to lower sizes for steeper size frequency distributions as expected. Here is another interesting output. This is the distribution of the orbital inclinations, where we can see for steeper SFDs, we have prevalence of prograde with respect to retrograde objects, which requires further examination. And as I said, we then took all our discovered objects from SORCA simulations and propagated their observability parameters to see which could be potentially observed by our Teled Milankovic telescope in Serbia, which is already a part of the CERSAG S2 in-kind contribution to the LSST for the follow-up of the bright LSST transients. Here are some just basic characteristics of our telescope. And unfortunately, our preliminary analysis show that this telescope has pretty limited possibilities for observing the discovered interstellar objects. Here you can see the fractions of objects that could potentially be observed by our telescope depending on different parameters such as size, frequency distribution, and brightness model. But you can see for some combinations of these parameters, we have some non-negligible fractions of objects that could be potentially observed by our telescope. And here I have some summary points. I thank you for your attention, and I'm here for your questions.
Thank you. Any questions? Yeah.
I've got one. So if this telescope has limited capabilities, what would be required to have more opportunities to observe ISO? Is it telescope size or location?
Yeah, it is 45 degrees north, and it is 1.4 meters, so we would need like a larger telescope on better position. But I think this is just a preliminary analysis. We will include many other possible synthetic populations because we don't know how the population of interstellar objects looks like. So we will have more results, and maybe for some combinations of the parameters we will have better numbers. But these numbers also show that this telescope could be potentially used for these observations.
Yeah.
Thank you. Gers Bauer, University of Maryland. You said you used 12 different models for comets. Did those include activity for, did those include models for activity for the comets? Active areas and yes, okay.
Yes, I have a backup slide for that. So here are those 12. So this is just 4 different options for the absolute magnitude of the comet, and another 3 different options that we use for this photometric index, which defines how fast the brightness depends on the heliocentric distance. But we will include many others in our future work. So this is just from the Cook paper from 2016.
Okay, thank you.
Yeah.
Thank you.
Thank you, everyone. That is the end of our first session. Can we thank all of our speakers one more time, please? Thank you. And just a few quick announcements. First, I'm sorry, I asked a question without introducing myself, which is what we're all supposed to be doing. I'm Amanda Sikafus from the Planetary Science Institute. And thank you to all the speakers for keeping to our time. We really are trying to keep on track. And thank you for bearing with us. We've had a few technical issues. We're hoping to swap out one of the cables right after this session to solve those online issues. If you do have questions, we encourage you to follow up. There was the Zoom session happening. There's the Slack channel. If you're here in person, please find people during the breaks and go talk to them. Thank you so much, and we'll see you back here in this room at 1:30 for the next session.
Hello? Hello? Why is coming also here? Why is coming here? One, two, two. Why is coming back this side?
Coming back that side.
It's getting out there and then coming back.
On my phone. I'm writing my program down, Papa.
Hello? Hello? Is your side too? This side too.
Why is this side?
I don't know why it's
You look what we watching. I'm walking onto the Zoom now. Okay.
Okay.
Let's see.
Hello? Is your side too? It's simple, but
Na kuhusu hawa na huyu kuna.
Hello? Hello? Hello?
Wapi Zoom?
Zoom yangu.
No, Zoom ozo tinda.
Unazotinda yangu.
Okay.
Na OP.
Na ozo sala awa iza owa.
Is that all?
Just wanna troubleshoot something.
Is that two? Two. Is that two? One, two, two, two. One, two, 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 two. Yeah. 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 One, two, 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 two. And that is out. You see? When we plug it and then coming back. Two. You see?
Musala is a rab. You know what pisses me off? Talking about Musala being the reason they phone ayo.
Et puis au lente. Two. Nafungula siko nani out there. Okay, go. One, two. One, two. One, two. Zoom in. One, two. Check. One, two. One, two. Okay. One, two.
One, two. Testing, 1, 2. Testing, 1, 2.
Can you hear me?
1, 2. Yes, I can hear you.
Just go out, go further out, like
Yeah,
go
we'll
away
do.
from the room.
Okay. Yeah. Okay. 1 2 1 2. Can you hear me?
Yes, I can hear. Can you hear us?
Yeah. Can you hear you loud and clear?
Okay, cool, sure. Thank you.
That we
Okay,
need.
sure.
Okay, great.
Cool. Sure. Go back. Get out from because you are on already. Yes. Yes.
1 2 1 2 1 2 1 2 1 2 2 1 2 1 2 1 2. Testing 1 2
Yeah, can
1
hear
2
you.
1. Okay, yeah.
Stefano.
1 2 1 2.
Stefano. 1 2. Yeah.
So you good, yeah, everything's okay. Yeah, yeah. What I want you to do, make sure you create a folder, you copy all your presentation that you're gonna do on the next one.
1 2. Yeah. Stefano. 1 2. 1 2. 1 2. 1 2. 1 2. 1 2. 1 2. 1 2. 1 2. Hey. 1 2. 1 2. Why is coming back? That is a problem. One, two, 1 2.
Oza zoom, oza zoom, oza zoom. Onde in na bango. Écoute, mais au out nanga. Yeah. Si ko tala ezo combiner pourquoi? 1, 2. Zoom. Yeah. Mais pourquoi ils ont combiné now? Yeah, EKI yebo. Yeah. Nakoyoka, mais c'est quoi pourquoi ils ont combiné now oyanga? Au monde. Yoka ils appellent bien té parce que ils ont des records non pas. Donc aux autres na zotinda zoom yango natindi ba mic nanga. Ye anatindi yete. Mais exactly. Mais c'est quoi yoka nan dengiza. What? Oyoki ndengisa. Siko zela. 1, 2, 1, 2. Oyoki ndengizo sal. 1, 2. Oyoki échanger. Mais kasi des problèmes natali nyon surtout pour bangonde. C'est quoi on a changé bo na che bo na longoli o na che. Et puis na kitisi pe na volume na bango. Au monde na kitisi na volume na bango. Pour le moment ils en ont honte. Ils are off. Mais yokana ndenge zo binana et pas nanga. Ezo loop. Bon si ko loop ezo salela. Ah wow. Zela. Na longa nan o iza at the B-link na bangwana. 1, 2. Ezoyaka. Ezoya. 1, 2. Ozoyoka nenzal liboso. 1, 2. Zela siko na formula. 1, 2. 1, 2. 1, 2. Ozomon yango pe ezomatisa volume 1. 1, 2. Yeah. Yo. Ezande kuna. Parce que natika ko sabo te eza c'est simple et puis eza link out. Ce qui est attaque. Nde yango wana na kati sikoyo enazotindela bango yango mais volume nango nde na kati nanu sikoyo mpona yoka mais ezaka ndenge moko nazotindela bango oyo ezaka inene ezali kosalaka bongo.
Yeah.
sikoyo son na yo eza na number 4 yango natindeli yo leki ezoya yango okendaki ka sikoyo
Est-ce qu'il y a un temps ici à faire ici? Moi, j'aime pas échouer dans ma vie. C'est l'unique chose que lorsque je fais des erreurs.
non les erreurs c'est pour apprendre non
Oui, c'est ce qui me fait à ce que je sois excellent. I don't waste time.
baerere yo yebi baerere biso tosala baevita monene kutu sali ya monene baboru mwana this guy don't like to risk
Huh?
not that much risk but he can invest.
Check, check. 1, 2. Hey. Ah, cosa. Moni.
So it's working? Yeah. So can the online people hear us through this mic now?
Yeah.
Okay.
Yeah.
Okay. I think maybe just too many people, so I'll just introduce the session.
Marco. How's it going?
We finally made it.
Yeah. Luckily. But without much sleep, but no, he worked it out. Yeah. Yes, no different flights, different problems. Yeah. I saw some people from Fiumicino coming onto the slide. But... Hey! Yeah, you have the chair for today, for this meeting. Yeah, and the next one. Are there any other people?
No. They don't show you everything. No, there are many more. There are many more towns than they show you.
Let's see how to draw.
Any other people coming? Yeah, just came in like straight from the airport. Yeah, but I just went to the to my hotel, and then yeah. How was the first session? It was interesting. Yeah, I couldn't watch it because I was on the flight. Exactly.
So which is the flight that got cancelled?
No, it was just fully booked, overbooked basically.
Okay.
The one yesterday. So
From where to where?
from Frankfurt to
Cape Town.
Yeah, apparently many people didn't make it on that flight, but luckily yesterday there were some spaces left.
Okay, so you had a seat and everything booked when you arrived.
Yeah, basically what I do is like a standby ticket because my sister is working for Lufthansa, so she can book me through their system in there directly. But it's a bit tricky because you never know if you're gonna cash it. Normally it should be fine for this one, like because there days or weeks before it was like 40 seats easily open, and then like the day before it was like a whole mess because some flights from US canceled and stuff.
Yeah, I know some people from the US. Like
that they flew over.
My ex-advisor, my PhD advisor, they told him he is stuck in Washington. He's going to be stuck for 3 days there.
Oh no.
Was he going
He still is?
He's not presenting, but he was expected to come and see. And he's not.
So he's cancelled.
Earliest he can come is at 5. I think he'll try, but he missed the whole focus meeting.
So it's 3 minutes, so should I session?
I was just noticing too, so the poster session also starts at 3, so we're going to go straight from here downstairs.
Yeah. Okay, good afternoon, everyone. Thank you for joining the second session for this focus meeting. We're going to start in 3 minutes. The session is titled Exciting Upcoming Surveys, the MPC and Alerts Streams. So in this session, we will start with 2 invited speakers. So they will each be 20 minutes, and then another invited speaker a bit later in the session. So we will start in 2 minutes or so.
Yeah, there's the wrong stuff is on the side. She asked ours, and I said,
Okay, I guess it's time to start. It's 1:30, so we can invite the first speaker, who is an invited speaker, Myungjin Kim, and he will talk about NSOS Alpha, the first Korean asteroid survey telescope. It's an invited talk, so 17 minutes plus 3 minutes of questions. Thank you very much.
Thank you. My name is Myungjin Kim from Kashi, Korea Astronomy and Space Science Institute. It's my great honor to have this opportunity to present our new telescope project. We call this NSOS Alpha. This is the Korean first asteroid survey telescope. I'm a leading project scientist of this project, and the other all person from Kashi. Let me start with this background. As you know very well, there are a lot of asteroids around the Earth's orbit. That might be dangerous if something happens, but only half of them larger than 100-meter class were found so far. Especially after Chelyabinsk event in 2013, the international joint response activity were really needed. And let me introduce the internal situation, I mean the background in Korea. Exactly 10 years ago, there was a Jinju meteorite event in Korea. It was the first full meteorite event on Korean peninsula. So at that time, our country was kind of out of its mind because the Korea is a little bit small, not a little bit, but very small country. So we don't have this kind of experience, and we don't have any rule or law related to this event. So Korean government began to pay attention to this kind of natural body event. So from 2015, Kashi was designated as a National Space Situational Awareness Organization. Then this kind of long-named act was made at the time, and we defined the collision of asteroid as one of the typical natural disasters, such as a typhoon and earthquake. So we also conduct this kind of activity, like a tabletop exercise and real training, as like a planetary defense conference twice a year. With this background, we start our project in 2019. The project has been budget has been approved, and during this period, we made the baseline design with NYR lab. But after this period, it's not easy to find the telescope manufacturer because just after COVID-19, the oil price was increased. So yeah, it took almost 2 years for the procurement process. But last year, we made finally we made a contract with IDOM, a Spain company, and now we are on the review process. Last April, we did the PDR, and we're gonna have CDR meeting in coming October.
We hope to start normal operation from middle of 2027. The project goal of this telescope is the discovering NEA, especially potentially hazardous asteroid. So when the normal operation begins, we hope that our telescope name will be listed in here. Yeah, the list of the planetary defender. Another important point is there NASA-funded survey telescopes are mostly located in Northern Hemisphere, as we see the last graph. We can clearly see this figure that in Southern Hemisphere region is empty in terms of the sky coverage from CSS G96 telescope for 1 year operation. This is the galactic region. So we will build our telescope in Southern Hemisphere. This is going to be first dedicated observation facility for NEA survey with a 1.5 meter class telescope. To achieve this goal, our key specification is like this. The main mirror should be larger than 1.5 meter and prime focus type. The F ratio is very fast optics, so it makes the field of view is around 5 square degree. Those specification is very similar to the CSS ones. We strongly collaborate with that team, and we choose the detector, choose a E2V 9K CCD camera as a detector with only one clear filter to maximize the detection efficiency. The mount is the equatorial type, and dome shutter style is conventional style like this. We are now working on making a survey strategy. So we investigated where the PHA located in the sky. Actually, this is the sky plot from 170 objects discovered in last year. To each object location information is from the MPC first discovery report. So those red line represent to the ecliptic plane, and this blue one is galactic plane. Of course, it includes the observation bias, but we again see a few objects in Southern Hemisphere. So we really need to make a telescope in Southern Hemisphere. And this is another figure from the same data set. So this is the longitudinal distribution of the PHA discovered in 2023. The blue and green line represent to the ecliptic latitude and declination distribution, and the red one is the galactic latitude distribution, and black dotted line implies the data wherein a uniform distribution is considered. So as you know, as you can see, the large number of asteroids are found on the ecliptic plane, and a fewer number of asteroids are found on the galactic plane because it's very crowded field region. So, of course, we should start the survey simulation with real annual population model soon. Actually, Kashi already has a 3 telescope network in Southern Hemisphere, as Nick mentioned morning session. So there is a Sutherland Observatory, and Australia and Chile. We already have a 3 telescope network, but it's only for the dedicated micro-ranging survey telescope. Actually, we asteroid team in Kashi use only a percentage of the telescope time. So we, from the weather statistics data, we clearly see the CTIO, the red one, is the best location for among 3 Southern Hemisphere sites. The weather clear night, number of clear night, and the seeing condition is the best comparing with other sites. So we selected CTIO Observatory here. This is the KMT-net telescope in CTIO, Chile, and this is the Blanco 4-meter telescope, and Lachi here. So actually, our tentative location is here, just nearby KMT-net telescope. We already had a meeting with ORA and NYR lab leadership people, and we visited there. Actually, they suggest 2 or 3 candidate location. Then we determine the exact location as I just showed before. Here, we're gonna make a telescope here. Then our division director, Dr. Sung-Gi Jo, and CTIO director, Steve Hascott, we're gonna shake hands, and this is kind of a cornerstone of our telescope location. And a site agreement is under review by ORA, and we hope to sign the site agreement within this year. Then we're gonna discuss for the construction work for the trilateral agreement between Kashi and CTIO and EDOM. I'm going to introduce our international partners. So we start to discuss about our telescope project with the CSS team and NYR team. Actually, CSS is one of the best contributor for NEA discovery, and NOAAREP has a very good skill for the telescope design. So those 2 partners are very helpful for our project. So for this CSS collaboration, we're gonna share the same software such as the moving object detection pipeline, and we're gonna share a similar scheduler and operation program. Also, we will do the research collaboration works. For the NYR lab, so they made a baseline design, and they will support in terms of the technical part. So they're gonna attend the design review meeting and fabrication test as well. Especially CSS collaboration, we attended the CSS monsoon workshop and discussed a lot of things. And next week, we will also attend this workshop remotely. We signed a research collaboration agreement and strongly collaboration with CSS team. And this is the brief construction timeline based on the RFP. So we are just here. This year is very busy to review the design work. So we hope to start from 2027, but yeah, something gonna happen when we make a telescope. Actually, we really need to follow observation network. I saw many talks in the morning session. There are lots of telescope projects in European side and other country. You know, the follow observation network is very important for NEA confirmation. But yeah, this is the world map, shows the telescope list that I ever used or that I have a telescope time. Actually, we are now building up to make a ENSOS alpha follow-up network. So anybody can have interested in participating this follow-up network project, please contact me right after this talk or during the IAU period. And this is the last page, and I'm happy to introduce the Korean first asteroid survey telescope, and it will be the first dedicated observation facility in the southern hemisphere with 1.5 meter class telescope. As I mentioned before, we're gonna start the observation normal operation from middle of 2027. So we know very well the game changer should become soon, but I can say that I don't want to kind of competition. I want to make a synergy in terms of the NEA discovery and planetary defense. So if there is a people who belong to the LSST Ruben asteroid team, please let's meet together, and we're gonna discuss a lot of things. Yeah, that's it. Thank you very much.
Thank you. Have you got any questions?
I have one. Marco Micheli from ESA Planetary Defense Office. It's just a question on the survey strategy that you're doing. From what I understand, you are going to be mimicking the Catalina strategy. So I guess maybe 4 images separated by 10-15 minutes each. Have you explored like things like synthetic tracking, like alternative ways of observing? And do you have any idea of the pros and cons for your specific hardware?
Yeah, actually, we are working on that survey strategy to make a synergy or better way to find a better way. Now we will do very similar to CSS1 for imaging, but yeah, if there is another way to approve, yeah, we're gonna select.
Okay, there's one online question. You sort of answered the second part, but the first part is, what is the planned limiting magnitude for the detections?
Yes, it's 21.5. It's very similar to CSS1, but more deep, I mean, until 22, around 22 magnitude.
Okay, we have enough time for one more question, which I'm going to take if that's... have you thought about running your pipelines on KMTNet historic data to see if there's any NEAs that you've discovered in that KMTNet data set?
Yeah. Actually, I'm a PI of the Deep South project that used the KMTNet telescope for the asteroid science. Our team does not have our own software for the NEA detection. So I know you using that telescope with the NEA science or asteroid science. So we're gonna discuss. We're gonna have a collaboration.
Okay, so I guess we're ready for the second talk, which is also. Sorry. Sorry. The next talk will be another invited talk by Luca Conversi, and it's titled NEOMIR ESA Space-Based Infrared Mission. It's also invited, so 17 minutes plus 3 for questions. Thank you.
Okay, thanks. So I'm here to introduce a new space-based mission that we are studying in the European Space Agency as part of our planetary defense activities. Does it work? This one. Sorry, which one should I use? Okay.
The laser pointer is a separate one. That one doesn't work. Oops.
So this is okay.
That one works.
Sorry for that. So okay, first let me introduce very briefly what is the Planetary Defense Office that we have in the European Space Agency. It's part of the Space Safety Program, and of course we take care of all the aspects related to planetary defense. So we carry out NEO observations. At the moment, mainly follow-up, but we also have in the near future plans to have a dedicated telescope for surveys. This is, of course, ground-based. And then, based on that, we compute the orbits and assess the impact probability of impact probability related to NEOs, of course. And then all of this is disseminated to the public, but also we interact with eventual protection agencies, plus, of course, we participate into I1 or same page campaigns, even if this is a bit not related to this talk. What I think it's important to stress out is a bit the different approach that we have in ESA in respect to what our colleagues in NASA have. So in our planetary defense office, let's say we try to focus mostly on the smaller asteroids, so let's say between around 40 meters of size, and meaning that what I'm writing in the slide is basically our internal mandate is that we want to discover all asteroids of 21.5 magnitude in any given night, which more or less corresponds to an object of 40 meters, which is 3 weeks distance. This, of course, depends on various aspects, and of course, it can all be achieved for objects that are coming from opposition, so from a night side. By comparison, let's say NASA is following the mandate given them by the US Congress. That was, I think, in 2012 or so, if I'm not wrong. And the mandate at the time was to discover 90% of NEOs bigger than 140 meters by 2020. We are in 2024, and we are way behind this goal. So we are below 50% of this number. And we already know that, I mean, simulations tells us that basically with only ground-based observatories, this is not achievable. And that's why NASA is planning, and will launch in a couple of years, 3-4 years, the NEO Surveyor mission. So what is NEOMIR? What is NEO Surveyor, and how does it change in respect to ground-based observatories? So from the ground, basically, all NEO surveys carried out nowadays, they are carried in the optical domain, meaning of course, we detect the sunlight reflected by the asteroid. This will not work for objects coming from a sun side, like the famous Chelyabinsk event. Mostly because only a small portion of the sunlight is reflected. Plus, if you're observing from the ground, we have the atmosphere which is preventing us from going very deep in magnitude. So the one solution is to go to space and to observe the thermal emission of these asteroids. These asteroids have typically an average temperature of around 300 Kelvin, meaning that they peak between 6 and 9 micron. The other advantage of doing this is that we will have less stars, less galaxies, so there is less source of confusion. And of course, the drawback of doing this solution is that the instrument, it's much more complex. So we will need to have cryogenic instruments, and also data handling the moment you go to space is a bit more cumbersome, data processing and so on and so forth. So this next slide is about showing what is, I will show later, how NEOMIR fits into this overall picture. So this is the position of impactors. It's simulations, of course, but it's positions of the impactors as time before the impact. So in the first in this first year, it's 1.5 years before impact. This is where they are at 1 year before impact. This is 6 months before impact. The Earth would be more or less here at 0, while here you have the sun. And then you see that, of course, when we are in this regime, most of them, they are along the ecliptic plane. And 1 year before impact, there is none at opposition, and 6 months, there are only a few at opposition. Still, if we check, if you overplot what we can do with ground-based observatories, we see that, and also with NeoSurveyor, we see that we could cover most of these objects. The problem is that if you're thinking about smaller objects, they can only be observed when they get closer than 6 months, unless, of course, you detect in a previous orbit, but in most cases, you only detect them in the impact course to Earth. And the situation changes like this. So it's the same plot as before, but between 3 months, 2 months, and 1 day. So you see that this, let's say, cloud of impactors is spreading all over the places. And that's exactly the area that we want to cover with NEOMIR. That is the expected coverage of NEOMIR. It's basically to observe a ring around the sun with an elongation between 30 and 60, 70 degrees. So again, this is what I was just showing. What is NEOMIR in a nutshell? So we started studying the mission 3 years ago in internal to ESA. Last year we had European industries studying the first iteration of the mission. And we are keep doing this for the next at least 3 years. Reaching the so-called, at least in terms of ESA engineering studies, we call it phase B1. So we are not going to implementation, that will be the next phase, of course. So what is NEOMIR? It would be a mission that it's a spacecraft that will be placed in the Sun-Earth Lagrange point 1, so let's say closer to the sun in this sense. It will observe, it will have a field of regard, so it can observe anywhere between 30 and 70 degrees of solar elongation. It will produce a huge data link, a huge amount of data, similar to what Euclid is producing, so it's 1.4 gigabytes per day. And it will launch by Ariane 6.2, since we finally demonstrated it's working. And we are possible late in the 2030s, so it's, at the moment, the target date is 2031. And as I said, the idea, the basic strategy is to do a ring around the sun, whose, let's say, thickness is still to be TBD. In terms of payload, it's a 3-mirror astigmat, so they have 3 mirrors that will provide a very large field of view of 1.7 by 7 degrees with a typical PSF of 3 seconds that is diffraction limited. As I said, it will cover a band between, it will be a single band covering between 6 and 10 micron using 2K by 2K infrared detectors. And the baseline is to have this infrared detector developed in Europe, but we know in any case that if this cannot be achieved, we can still go to Teledyne and basically ask them to have the same detectors that will fly on NeoSurveyor. In terms of thermal, as I said, this is one of the most demanding part of this kind of missions, is that you need to cool down the whole instrument to 55 Kelvin, and specifically the detector need to be cooler than 40 Kelvin. So they're still doing an analysis if it is better to have a fully passive or a combination of passive and active cooling system. So in terms of survey strategy, that's also related to what Marco asked in the previous talk. Let's say the standard, at the moment, the standard baseline is to have the so-called classic strategy design, where basically we will observe one ring around the sun. We will observe one field, and then we will complete the ring 4 times. So basically, we will revisit a given field every about 3 hours. And the moment we have at least 4 revisits, we can try to detect objects and build tracklet out of it. The advantage of this system is that it's a proven concept, and we don't generate so much data. The disadvantage is that the NEO must be detectable in every single frame. And of course, the moment we are talking about NEOs that are approaching the spacecraft, they will move very fast. So they will not be point-like anymore in a typical 1-minute exposure. Then there is the trade-off that we are still analyzing. It is better to have a single ring repeated with a high frequency, or having multiple bands that we want to observe, but then with less frequency. So again, it's a trade-off of how many objects you gain, I mean, how many potentially impactors you would find with a larger, exploring a larger field of regard, versus how many you would lose because they just sneak between one repetition and the next one. The other option is to go with the synthetic tracking technique. I guess most of you already know it, but basically the idea is that we would go to a given field, stay there for a few minutes, but taking much shorter exposures. Typically could be 10 seconds, 15 seconds exposure. And then in post-processing, we stack them trying different motion vectors. So the moment the motion vector matches the one of the asteroid basically would pop up. The disadvantage of doing this is that, of course, we will have much higher data volume, basically. So the next thing that we did so far was to study the NEOMIR capability in detecting and finding potential impactors. And so we have a series of orbits. So actually we have 3,000 orbits of impactors provided by Steve Chesley. It's not really distribution in the sense that it's the frequency of the event is not representative, but it's a distribution in terms of orbits. So let's say the orbit that we have, they represent the actual probability of where the objects are coming from. Since it's only orbit, there is no size associated to it. So we tried 2 different sizes for all objects. So we tried 35 meters and 15 meters. And then we compute the ephemerides of this object between 60 days before impact until the day of the impact. And we try to check if NEOMIR was capable of detecting them. So out of these 3,000, only 1/3 were passing in the NEOMIR field of regard in the last 2 months, meaning that the other 2/3, of course, they are coming from outside, so they would be in principle detectable from ground-based observatories. What else? So here, then in terms of signal to noise, so in order to determine if we could find this object, we impose that the signal to noise is to be bigger than 5. So the signal is just the fact that we take a thermophysical model provided by Marco Delbo, and basically based on the positions of the asteroid, how far the asteroid is from the observer, how far it is from the sun, and plus the geometric the angle between these three elements, we could determine what is the expected flux from the asteroid. in terms of noise, the biggest three contributions, I listed them here. Two are, let's say, instrumental, so the detector, the current, and plus we have thermal and stray light contribution, and this, of course, we have initial indications of what could be. But then the highest contribution is the sky background, especially zodiacal light. And so for this, we used the model provided by the IRSA IPAC model. But basically, we could estimate what is expected zodiacal light in every single for every single observation NEOMIR would do. So based on that, we try to estimate then when and if we could detect these impactors. And so we find that for the 35-meter case, we have a success rate of 92%, meaning that, yes, we could detect most of the objects, actually all of them, and typically around, let's say, 1 month before impact, even if 180 of them are detected in the very last 2 days, so leaving very short amount of time in order to react to this kind of impact. The moment we reduce the size, then of course we'll be able to detect them when they are closer, so that this compensate the loss of signal to their size. And so we drop to 82%, and still about 200 of them, so 1/5 of them discovered in the last 2 days. Last but not least, we also investigated the Chelyabinsk. Specifically, we checked if we were able to detect Chelyabinsk, basically, with NEOMIR. So here you see the orbit of Chelyabinsk. This is in the Earth reference frame. So here you see that in the last days, Chelyabinsk is going, this is its orbit, while in green you have the region that NEOMIR would scan. And this heart shape is what a typical ground-based survey would be able to detect. And so you see that, of course, we would only be able to observe it in the last very few days. And this is explained in this plot here, where basically you have the elongation versus signal-to-noise ratio, and you see that it's only observable in the very last few days when basically Chelyabinsk would pass by the spacecraft. So last but not least, it's what if we detect something with NEOMIR? Can we do follow-up? We are still investigating this. This is preliminary. But long story short is that we believe that we could recover about 40% of NEOMIR detection from either hemisphere. I did not check honestly yet the cross-match, so it's not that 80% of the objects will be detectable from the whole planet. It's going to be a bit less. But yes, the work ahead is basically we need to, the other thing we need to understand is indeed if NEOMIR itself can determine good enough the orbit to assess the impact location, or if we need ground-based observatories. This is still an open question. And my last slide is about roadmap. As I said, we did in the past 3 years this initial, the so-called phase 0, phase A study. And now we are entering into the second phase. And by end of 2026/5, I should update maybe this slide, we will end the reach of phase B1. And then the next ministerial, we will see if we get approved for actually implementation and launch in 2030s. So that's all. Thanks.
Okay, thank you. Any questions?
If you detect them only a few days, sorry, there, okay. If you're detecting things only a few days out, how quickly do you get the data down and process it, and can you issue an alert? Have you thought about the
we thought about it. So let's say the baseline is that we download data every 12 hours. So we have twice a day a downlink, and then the data could be processed. I mean, what we requested right now is from the first detection to the actual alert, we should have 48 hours, but usually I'd say that we could analyze the data in less than 12 hours, so I would say 24 in total.
Sorry, in your last slide, I didn't see about the scheduling about the ministerial. Is it the same ministerial that will also assess for the Ramses mission, or?
Yes, that's correct. So yes, indeed, the ministers have to decide which one of the two have to prioritize, and if they decide to give priority to Ramses, then NEOMIR would still be studied, but then it will go to the next one. So indeed, honestly, there's no money to do both at the same time. Yeah. But if you go with Ramses, then NEOMIR would shift by, let's say, 3 years. That's the baseline. Yeah.
If you detect an impact 2 days in advance, would you start to evacuate areas or do warnings? Suppose you had discovered the Chelyabinsk impactor 1 or 2 days in advance, what would happen?
So the idea, I mean, in the case of Chelyabinsk, it probably would be as simple as notifying people with simple things, just like, stay away from windows. So the Chelyabinsk event, for example, did not destroy any building by itself. Many people were injured just because they were watching the event, and then the sound wave, shock wave came and destroyed windows. So just giving some instructions, it would be good enough. Then, of course, we discovered a 1 meter object falling on the center of Paris 2 days before it happens. Honestly, there is not too much you can do it, I guess. So it depends on various aspects, but yeah.
Okay, thank you very much. We're out of time. Let's thank the speaker once more. And now we have the third talk. It's from Gersbauer. Planetary Science with the Sphere X 0.7 to 5.0 micrometer solar system object catalog. This is a regular talk, so 7 + 3 minutes. Thank you.
Great, thank you. Thanks, Marco. Oh, wrong slide. Wrong slide set. You should. I loaded it up. It should be Sphere X. That's my poster. I could talk about the poster. Then what will I do for my poster? Talk about the talk. Oh, it's all right. Do you want me to come? Oh.
Okay, so small change of plans. We are going with the fourth talk instead, and then we'll wait for Gerbs for the next one. So the next talk is the third and last invited talk of this session from Federica Spoto, and it's Minor Planet Center preparing for the increased flux of discoveries expected from LSST. Thank you, Federica, for going on as the next speaker. Thank you.
Okay. Good afternoon, everyone. As Marco said, I'm Federica Spoto. I'm the project scientist of the Minor Planet Center. And so I'd like to thank the organizer for inviting me and giving me the opportunity of talking a little bit about how we're getting ready for LSST and NEO Surveyor in general, the new surveys. A few words about us. So the Minor Planet Center is the single worldwide location for receiving distribution and positional measurements, and we're also our goal is basically to work as a clearinghouse for everything that is observed, and then we give designation for what we think is new. We work under the auspices of Division F of the IAU, and also we are part of a functional subnode of the small body node of NASA PDS. As of today, there are 13 people working at the Minor Planet Center. You can see all of us up here. And we're divided into astronomers, software developers, and IT and database specialists. You see Matt Payne is going to be here tomorrow. His flight was delayed. He's the director, and as I said, I'm the project scientist, and Chris is our technical manager. So mostly we're working towards getting ready for the new surveys, and I wanted to give you like a brief introduction about that. I guess the main question is like, how are we doing? And so if you are asking yourself, what would happen to the MPC if LSST started today? Would we survive? I'd say that the answer is yes. We wouldn't crash, which is already a good starting point. And we got to that point thanks to a long, long way of like long job and a lot of things that we did in the last years. Just to give you an idea about how many observations we get every day, every month, this is like an histogram of the amount of observations we received in the last 1.5 years. The y-axis is in million observations. We maintain a database at the moment that contains a little bit more than 440 million observations, and we receive more or less 30 million observations per year. Now, we have been having days in which people, and like in general surveys, dumped on us millions of observations without telling us. And so that is more or less what LSST would do. In that case, we would know. So the system worked. It's not that it crashed. It was just kind of like a little bit clunky, a little bit slow. Processing was slower, receiving was slower, but we made it. So that was a good, like, stress test in the sense of like what would happen when you get this type of like large volume of data. It hasn't been, let's say that now it doesn't have any problem. It had problem before, and so we're trying to tune our way of like receiving so that, for example, now we prioritize NEO submissions. So if you submit something that is new and it's an NEO and it needs to go on the NEO confirmation page, usually it's prioritized. Also, sometimes users don't put the right keywords in the submission, so we have also checks in place to be sure that we're not missing NEOs in that sense. The second point was like, we need to be ready for the format and how people want to submit observations to us. And a big change happened when ADAS was creating. Now, ADAS is the Astrometric Data Exchange Standard. It was created around 2015. Let's say that it became really big during 2017. The point is that MPC used to receive and like disseminate observation in this format, which is called MPC 1992, and it's a fixed 80-column format. It does its job, it contains everything you want, it's just it doesn't have a lot of new information like uncertainties on the observations. So that's why ADAS has been created. The main advantages was like more information can be sent to the MPC, or in general can be given to observers or like orbit computer centers so that it's easier for us to understand what has been observed, what has been measured, and how. As of for now, the ADAS is the only format that is like used internally. It's the main format that we use to like do orbit fitting, receive, in some sense disseminate. It will come later, but this is because it's very stable. It's under a public GitHub repository, so everyone can actually open issues or ask for requests. We work in collaboration with other people, including JPL, to maintain this repository. So it's something that we're really working on, and you can see here. The blue bars is like observations submitted in MPC 80-column format. The red bars are like submitted in ADAS. You can see how things changed in the last like 6 years. And so now the majority of the observation, especially from the big NEO surveys, are just submitted via ADAS. And this is what LSST and NEO surveyor are gonna do. When I said we're disseminating the observation, it's like the MPC has a lot of different publications that we maintain, which include daily orbit update, mid-month, monthly, and they're still based on flat file type of like scenario. But we're trying to develop new things so that in the future, our data will be more easily accessible. And one of the things we developed recently is called MPC Explorer. Now, if you're slightly familiar with our website, we have a functionality which is called DB Search. Basically, you put in there a designation of a minor planet or a comet, and it will give you back all the information that we have, like a summary of all the information, discovery, observations, and orbits. This is based on the whole system, so this is based on all orbits and all formats. It doesn't include, for example, orbit uncertainties. It won't give you ADAS observations back. It doesn't contain all the designations. For example, you can't look for search for NUCP objects. You can't search for natural satellites. You can do that with the new one. So this is already available now. It's available and everything is based on APIs. And at the moment you have this type of information available. The designation identifier, which is everything that you find in here and much more in general if there's more to say. But for example, let's suppose that an object has been linked, you get secondary designation. If you have a dual status of something that was an asteroid and then turned out to be a comet, you have both information in there. And also you have natural satellites and comets all in the same place. You can search for whatever type of designation you want. It can be a number, a probe ID, packed, unpacked, whatever you might think of. And we recently added NEOCP objects. Now, for the moment, it's pretty easy. You just get back the track sub because there are not a lot of information available. But the nice thing is that you get back all the observations in both format, ADAS and AT column. Now, the format of the observation is exactly the same if you're looking for NEOCP tracklets or designated objects. And as I said, API are also available associated, so you can create your own code to actually retrieve all of that. We're planning to add additions, so we want this Explorer to fully replace the DB search, so that it's going to be super easy for the users to use it, we hope. And so we're going to add orbits, discovery details, and plus summary, and everything that you can actually find. And the other point is that, this is a single object type of search, but you can actually get access to our whole entire database through SBN. And so we're replicating some of our main tables to SBN. And these are the observations table, which is ready, current and number identification ready. Primary objects, which means everything that has a primary designation is there. We're working on the orbits, and when we're working, orbits will be available with all full covariance matrices, non-gravitational perturbations, uncertainties. So everything that before wasn't available, we actually now computed at MPC. It's just, the current format wasn't able to give it to the user, but we're working on that. Plus, we're trying to get better documented everything. So the website also is a better documentation, and we keep working on it. So in general, if you have any requests, I'm more than happy to implement it. Talking about orbits and new designations, we moved to the use of ORFIT software entirely at the MPC. For those of you who don't know, it's a public software that was developed initially at the University of Pisa by Professor Andrea Milani. And now, the MPC will soon release its own version. It will become public, so you can do basically the same computation that we're doing, including linking and get residuals and everything. And this is done in collaboration with the ORFIT consortium. All our major automated processes are automated right now. That include a number NEOs, main belt TNOs, number, same thing, identification and recovery pipeline, and single MPEGs. Now, single MPEGs appear twice because some parts is still automated, some part is still manual. I'll go into that. But the main advantages is just as I said, we're not able to still show all the data that we are actually computing, but we do it internally, so we're able to get better handle of bad observations, use and publish soon the uncertainty for the orbits. We can use perturbers up to the ephemeris. We use internally non-gravitational perturbations, so we get Yarkovsky effect, which makes it easier to do linkages or to do recovery observations. And also we can use highly accurate astrometry in the orbit fitting, for example, Gaia or occultations if needed. I said the single unpack is mostly automated. Part is automated, part is not. Let's say 50%. So we've been working a lot on this NAP code, which stands for NEOCP automatic processing. And basically what happened is that when there's an NEO or an object on the NEOCP, which could be an NEO or an far object, it needs to be unpacked. And before that was completely manual. So there were people that were checking this list every day and that were trying to make it. Now, we created a code that basically is automatically able to scan our list of NEOCP objects and every 10 minutes, and it can decide with a lot of different checks if the object can be unpacked or not. So a lot of different checks were we don't want to, unpack directly imminent impactors or something that could be potentially very interesting because we want to double check. So there are a lot of checks in place in that sense. Some checks include, for example, that if we have linking information, we want to check that they're correct. Difference in magnitude between the object and ITF position, geocentric score. We don't want to unpack objects that, for example, are artificial. So we'll double check a lot of things. But as you can see, now we get almost 40% of the objects that automatically impact. And so that removes a lot of manual work from the people working at MPEC. There's some still work in progress, which I find pretty interesting. Okay, one is still more checks. We don't want singletons at the moment. But the other one is like, when is the best time to actually impact an object? Like at this, as of today, we don't impact anything that has less than 24 hours, just to be on the safe side. But when is a discovery actually good? Where we can impact it is, you know, if you have a close encounter, the orbit is usually well over determined, and so we don't need 24 hours observation. So there's some time of threshold that we're trying to understand, which I find pretty cool in that sense. So this is just something that we've been working on. It's way more than that, but now the point is like, what are we gonna do? Like, what are we actually working on right now, and how is this gonna help us like getting ready? First thing first, when I said we won't crash, that is correct. One thing will crash though, which is like this SPACT provisional designation. And this is because, I mean, if you don't know, it's a general way in which we designate objects when they don't have a number. That includes information on the year of the designation, the part of the month in which it was, and it's SPACT because it needed to fit in the 80-column format. The point is like, it is estimated that LSST will discover approximately 250,000 objects per month. Even if it's not like that, it's okay. Even if it's less, it's fine. not a lot for us, because this SPACT Prov ID only supports 15,500 new designation per half month. So we can get up to 30,000 a month. I mean, even if this is not correct, still it will break it. So the point is like we had to come up with a new extend packet scheme. There's some information about it that went out in the newsletter. We will like it's in the documentation. I'm not gonna go a lot into like what we did, but it's basically like we add an underscore and then everything else is mostly like a base 62 way of converting this type of numbers. So let's say that this is in some sense resolved. So that was one point. Second point is about the software. We've been going through a lot of changes at MPC according to the new standards, and we wanted to move to be actually something that was like able to use the software in the proper way. And so we're migrating towards a database-centric system, and you saw it with the MPC Explorer. We're migrating our receipt system to AWS. Orbit feeding queues are restructured to use Docker and RabbitMQ so they can be scaled up easily. And then as a part of the work in progress, we're thinking about creating a new orbit standard that will be the new, let's call it ODIS, which is like orbit data exchange standard with respect to ADAS. But that's the idea is that the MPC will move it forward and try to propose to the IAU. The website is following new standards, and so also, like, I know that for a lot of you, it will be pretty easy to say, but all our software is now under version control. That wasn't the case at the MPCs. It's been a big change, which actually helped out a lot maintaining it and, like, also make it public when we're going to make it public. The other pretty cool stuff that we're working on is the hardware side, which is virtualization. So virtualization basically enables the hardware resources from a single computer to become like your cloud. So we're creating an internal MPC type of cloud that it consists of some virtual machines, like some actual physical machines, and plus from them, you can spin up a lot of different virtual machines. And this is like easier for like processing a huge amount of data, but also for disaster recovery, because if something goes down, you can always get it back. The hardware setup is almost completed. We're working on setting up the virtual machines. Some of you might ask, what about your current services? So we're working about towards a new version of the NEOCP that will be more like Scout style if you've been using JPL Scout. So that is going to be part of the Explorer. That's why we started with the observations of the objects on the NEOCP. It will get better. And then also will contain comparison with Scout ephemeris. So we hope it will make it easier to do follow-up and like observations in case to understand what the differences are. We're working towards MP Checker and a new ephemeris service, still gonna have API type base, is gonna be part of the Explorer. And the idea is that when we have a consolidated orbit table, then everything will come from there because we will have good orbits, and then we will start like saving Chebyshev polynomial in database tables so they're like fast and easily accessible. So we hope to improve that for our users so it will become easier. And we're also thinking about additional tools like improving our negative observations report so that people in case will be able to actually report part in the sky in which they couldn't find the object, and so it will make it easier to do follow-up for the NEOZP in case you want to prioritize certain objects or like discard some others. And again, adding this over information also in the form of database tables. So just to conclude, we spent a lot of time in the last years trying to improve our current services and make it better for the community. That includes documentations, APIs, moving towards the new standard and make it so that it's easier for us to maintain it and it's easier for the user to actually get the information from us. We will keep maintaining some of our main services, like for example, the publications at the moment, because we know they're useful. It's just like that from our point of view, they'll be actually come directly from the database and not from like flat files. We want to move away from the flat files because that won't be acceptable, like sustainable for LSST when we get this huge amount of data. And also, like as I said, we adopt a new software standard that I hope will help us like move it forward toward the future. And just to conclude, if you want to keep yourself up to date with what we're doing, we actually write a newsletter every month. The newsletter is available on the website. It's under like new newsletter, but we also send it out through like MPCML and also MPML, just in case you receive it. So that was my last slide. Thank you very much.
Excellent, thank you. Any questions?
Can I ask 2 questions? Well, the first one is prior to the ADIS dates, and also I think that's the same for Marco. We've been submitting 80-column format astrometry with uncertainty written in the COM lines. But recently when I downloaded our old submissions, we realized, well, using the MPC Explorer, we found that the uncertainty information has been stripped. So I'm wondering if there's any possibility to, for MPC to check those COM lines, which might contain uncertainty information in the past.
Right, that might be a problem. We might talk a little bit about that because I know that was a way in which things were done before, and I'm pretty sure we have files somewhere, just everything was like saved into the database, and when they save it, that part was not maintained because of like the way in which the format was. But if we are able maybe to find that information, or if you have it and you wanted to submit to us or tell us like what we should look into, we could find a way to put it back. Okay.
My second question is, I wonder what happened to the Soho astrometry. You know, there were in the past. Well, when Brian Marston was the director, he had been publishing all those astrometry, but
yeah, so we've been working with the Soho team in that sense. We're waiting a little bit for them to produce ADAS, just because when they put uncertainties into ADAS, we turned out that it was pretty easy to do orbit fitting because they knew. And I'm pretty sure that we're communicating that to Brian Marsden. It's just like, we don't have that information available from the files. We tried to do some pretty flat, like RMS, and it doesn't work for all the objects. So since they know it, we asked them to produce ADAS and give it to us. And then once we have it and we tested it, I'm pretty sure we were able to produce all the different orbits. Yeah, it's on our to-do list.
Thank you. Let's thank the speaker again. We don't have time for more. But I guess there are many more questions, so please.
Great, so we go back to the third talk now. Gerbsbauer presentation should now be available. Looks like yes. The title is Planetary Science with the Sphere X 0.7 to 5.0 micrometer Solar System Object Catalog. Thank you, all yours.
Thanks, and thanks to the prior speaker for swapping. Thank you. I just wanted to introduce you to some of the solar system science that's going to be enabled with SphereX. If you're not familiar with SphereX, SphereX is a NASA astrophysics mission, MidX mission, which means it's kind of a medium-small mission. And its goal is to map the sky spectroscopically between 0.75 and 5 microns. The astrophysics goals are all aligned with there are several areas in which they're aligned. There's cosmology, there's galactic evolution, and there's volatiles in exploration of volatiles within exoplanet systems. But there is also a large amount of solar system science that will be enabled by this mission and this satellite. This is the Solar System Working Group. It's small but dedicated, and let's see, I hope I'm, does this work? No, the other one. The green, okay, thank you. All right, so that's a cutaway of the SphereX spacecraft itself. It has a 20 centimeter telescope aperture, which is smaller, considerably smaller than, for example, NEOISE, but it has also a very large field of view. It is following a kind of a NEOISE strategy, so terminator pole-to-pole orbit, looking out at 90 degrees elongation, but the large field of view means that the dwell time is going to be larger, so about 120 seconds on a particular region of the sky, and that will allow the smaller aperture to actually achieve sensitivities that are basically equivalent to WISE, so and NEOISE. Okay, so the way it takes its spectroscopy is a linear with a series of linear variable filters in 6 different channels, and the spectroscopy is non-simultaneous. So as the object may fall on different rows, it's different. Each row within a detector has a different wavelength sensitivity, and then so objects on the sky fill in rather neatly as it conducts its survey of the sky. However, for the solar system objects, which obviously don't move at sky rates, the density of the coverage in wavelength is variable depending on the object. So again, this is just the basic geometry of the survey. The successive areas and exposures do overlap, and so you do get some buildup of density along particular regions over a visit. This is just the wavelength coverage versus the mission day. It's a 2-year primary mission, and again, this is just what we call a waterfall chart, and these are all various different objects in the sky. So some are covered more densely than others. But in any case, there will be some knitting together that we'll have to do for the spectra, and we'll get into that in a second, just in terms of breaking down the steps. This is kind of a brag chart of what is going to go on with the survey, but I think for us, the most important thing is in this talk is this. So we're expecting to get about 100,000 objects, spectra of 100,000 different objects, and they will cover, of course, a very interesting diagnostic wavelength regime where you get mineralogical features on asteroids and the ability to do asteroid taxonomy based on those. And then, of course, you have various organic features and volatile ices that are within that region for comets. And then, of course, also some very important emission lines, including PHAs, and of course, water and CO2. And just a reminder that CO2 is only detectable from space-based craft and emission. And then CO2 is difficult, but will be much easier, of course, for SphereX. So it'll be it's estimated with the sensitivities, about 80,000 main belt asteroids will be seen detected and measured with spectra by SphereX, and that will, of course, enable taxonomic classification across these objects pretty easily and quickly. And again, a lot of emission lines for comets We expect to get about 200 comets during the prime mission of the survey, as compared to 18 and the handful, which are growing, admittedly, that have been observed by JWST. There are about, it's estimated that there are about 10,000 Trojan asteroids that will fall within the sensitivity regime of Sphere-X. Several Centaurs and KBOs will also fall within that regime, and you'll be able to get, of course, spectra with several absorption features of interest. I guess I'm running out of time, so I better move through this. One other thing that is, I think, of particularly unique interest is that Sphere-X will, for the first time, spectroscopically map, thank you, the inner zodiacal light. That is, of course, the light formed from dust that has been shed by asteroids and comets in the interplanetary region. And then also we expect to run across many PHOs and observe the spectra photometrically any interstellar objects that fall within our sensitivity regime. If Oumuamua were flying through our solar system when Sphere-X is active, it would have detected Oumuamua and been able to categorize it, at least at the longer wavelengths, with respect to its spectral type. So this is just how things will be knitted together. We do forced photometry, so we place apertures basically on the predicted location of the asteroid or the comet, and then we extract the photometry at each particular wavelength, and then after we've extracted it and removed artifacts, we then do a distance correction, then a phase correction, and then finally a rotation correction, and this will fold in all available sources of information for particular objects, including Sphere-X itself, of course. So there's a lot of synergy between surveys and different ongoing missions. LSST and several of the objects discovered by LSST and NEO Surveyor will be accessible to Sphere-X. Sphere-X will be a good way to vet objects for JWST, more focused and targeted observations. We'll, of course, see some of the Lucy targets and run over Psyche as well. And this is just, again, kind of a summary of all of the different things that I've mentioned. And just to finish up, this is just a pre-assembly pictures. It's been delivered already to BAE, and we're looking forward to its launch in early next year. So thank you. And
thank you. We've unfortunately run over time, so I'm going to ask that people approach the speaker during the poster session to ask questions, but let's thank the speaker again.
Thank you. Our next talk is the only online one of this section. Let's see, is David Trilling on the line and connected? I see him here, do I?
Could you share your screen, David?
Okay, and the title is the Solar System Notification Alert Processing System, SNAPS. Thank you. Let's see if you can hear you.
Do you hear me and do you see my slides?
Yes, loud and clear, and we see you and the slides.
Perfect. Thank you very much. Good morning, everybody. I'm sorry I can't be there. Thanks to the organizers for making all this happen. It seems great from my from my distant perspective, it seems like a great meeting. I'm going to briefly this morning tell you about the Solar System Notification Alert Processing System, SNAPS. So probably many people in this room are thinking about the big data revolution, coming with ZTF, which is this Wiki Transient Facility, LSST, and so on. So ZTF is presently producing all sky data and a public alert stream in a kind of pre-LSST manner. And LSST, of course, is coming sometime next year, depending on exactly how optimistic you are. And I think most people probably know that this is so much data that computational approaches are essential. You can't look at individual images to do science. So here I'm going to introduce just briefly the Solar System Notification Alert Processing System, SNAPS, which is a downstream LSST broker. I won't go in many details here, but this is our SNAPS architecture. And so you see at the top, data is coming in from some source, which could be ZTF or could be Atlas or LSST or anything else really. Either we can listen directly to a stream into our database, or we can listen to an intermediate broker, in this case Antares, which then rebroadcasts the solar system only part of the alert stream. Lots of details here, again, that I won't really discuss, but there's two main channels here. On the right side in red is real-time or nighttime outlier detection. So an object that does something strange during the night, for example, appears to become active. And then on the left side in the blue is daytime or population outliers. And these are objects that are intrinsically different from other objects in the population. I'll show you two examples just briefly. There's a lot of papers here shown on the left side, and you can track those down as you like. Okay, actually, I just said this. So again, real-time outliers and daytime outliers. The real-time are objects in the transient universe, and the daytime outliers are objects that are intrinsically unusual. And these papers are, emphasizing both of those. Our population outlier work is more advanced than our individual outlier work, so we're really focusing in the next 12 months on the individual outliers, and there'll be some results coming fairly soon on that. Okay, I just want to quickly emphasize what SNAPS does and what SNAPS does not. So on the left, you see what SNAPS does. We ingest observations of known asteroids. We're deriving properties for each of these asteroids, like its color, its rotation period, and so on. We have a value-added catalog where we're attaching, for example, 2-mass colors or Sloan and MPC properties and so on to those objects. And we're identifying outliers, as I just said. What are we not doing? We are not discovering new solar system objects. So when we receive an alert packet, which is a description of an observation, it is attached to an object with some designation. Okay, so if it's not a known object, then somebody upstream from us is doing that work. Somebody upstream from us is doing the work to attach an observation to a known object. If it's not known, then we don't receive it. And then later on, objects get matched through LSST, linked, as Federica said, and so on. And then in the future, we could receive information about that object. So we do not discover new objects. At the moment, we're not ingesting comet data. There's no bias against that. It just was slightly different. And so we started with not comets. And we're not working on non-solar system objects. Okay, what's the state of SNAPS at the moment? We have about 10 million asteroid observations. These are from ZTF, although we have the ability to ingest from other surveys, and we have done that at a small scale as sort of a test case. We derive properties for any asteroid with more than 50 observations, and that's about 100,000 unique asteroids right now. And of course, it grows every day. LSST is going to be about 10 times that, and within the first few years, and maybe about 50 times, by the end of the 10-year survey. So I'm going to give you quickly examples of our real-time or individual outliers and our population outliers, just about 1 minute in each case, just to show you some stuff that we're doing. So here's an asteroid that we have in our database. On the left here, I'm showing Julian date on the bottom axis, and absolute magnitude. The two colors here are the R and G band, G and R band data coming from ZTF. And on the right, same data, but now I'm plotting heliocentric distance on the bottom, and again, absolute magnitude on the vertical axis. And we have a little time arrow here, and the star shows you where perihelion is. So on the, maybe my mouse will work. Anyway, on the left, the object's, on the left plot, the object's moving left to right. On the right plot, the object is actually moving right to left towards perihelion. And you can see in absolute magnitude space, the object gets quite a bit brighter as it gets close to perihelion and then fades shortly after perihelion. Here's that same object on the right side, Julian date and heliocentric distance. And on the left, I've got these postage stamps. And you can see as we get closer to the sun, the PSF starts tight, and then it gets much fatter as we're closer to perihelion. Obviously, this is an object that is slightly active close to perihelion. And then the PSF starts to condense again after perihelion. Okay, so it's an active asteroid. It looks just like we would expect. In fact, I'll skip that one in the interest of time. That was an individual outlier, so an object that changed its own properties from day to day or from observation to observation. Here's an example of our population outliers. We're generally working in a 15-dimensional feature vector space. We have several different flavors of outlier detection, and I'll refer you to Mike Gowanlock's paper that was just published a few weeks ago, maybe last week, on all of this work. This is just sort of the summary. We have 4 instances of the same feature vector space. So this I'm just showing 3 dimensions here, which is amplitude, rotation period, and color. And here we have our 4 different outlier detection schemes. Blue shows inliers, red shows outliers. And part of this is a computer science exercise to understand what's our best outlier detection scheme. But there's some science here as well, which is to identify objects that appear to be outliers using multiple different detection schemes, like there's probably something actually intrinsically interesting about those objects. These are ones, again, that in this amplitude period color space are unusual compared to the ensemble population. Okay, so here's my last slide. Where are we going in maybe the next year or so? As I mentioned, our real-time outlier detection, we're focusing on our efforts on that over the next 6 to 12 months. In particular, the algorithmic development there. Our public-facing webpage and API are coming. And also, as part of that, we'll be producing an outgoing alert stream for real-time and population outliers. So you have a telescope and you want to know about active asteroids, we're going to send out alerts and you can say, oh, well, here's one. I'm going to go observe that as a follow-up target. Our nighttime and daytime processing is, I would say, semi-automated right now. And so we need to just put that in production mode. And finally, we think we're going to be ready to operate at LSST scale in a year or more, and time will tell. Thank you very much.
Okay, thanks, David. Any questions? No questions from the audience, David. Let's thank David again.
Okay, so is this working? Yeah, maybe. So the last talk is from Colin Snowgrass, the Adler alert system for solar system transient. And it's in person and 10 minutes, 7+3 as usual. Thank you, Colin.
Okay, thanks very much. Yep, thanks very much. So I can tell you about Adler. This is similar to SNAPS, is a broker system or related to a broker system for filtering LSST alerts. I'm one of the joint leads of this, along with Meg Schwamp, Belfast. Siri Optum, who's elsewhere in this meeting, is also involved. But the main people who are doing the work on this are postdocs funded to work on this, Steph Merritt at Belfast and Jamie Robinson at Edinburgh. So most of this is their work. Okay, so Adler is a classifier system for LSST alerts. So the idea is it's going to flag odd behavior in solar system objects, looking for anything that is changing, that is transient. And so we're going to ingest the LSST alert stream of the millions of objects that we're seeing with LSST, and identify things that look different on the same day. But then also the tools that we're going to develop to do this, that are going to look for odd behavior, are going to be available as public standalone tools that you can go and use. And if you're a member of the Ruben community and have access to the Ruben Science platform, you can go and run these tools directly on the Science platform, directly on Ruben data. So these are common tools that anyone can use. Okay, what are we looking for? We're looking for solar system transients. So there are a lot of different types of this. Unlike SNAPS, we are interested in comets. I'm mostly a comet person, so I'm very interested in comets that occasionally have outbursts and suddenly get much brighter. So we've got pictures here of 17P Holmes, which was obviously a very large scale one. The graph there for 7P. This is a more typical comet that has small outbursts of magnitude, fraction of magnitude on a very regular basis. There's also activity in centaur objects like Chiron, where you see activity in its enhanced brightness over a longer period of time. But from orbit to orbit, you suddenly see it's brighter. So things like that, looking for changes in brightness or changes in appearance. We're interested in things that are active asteroids or main-belt comets, things that look like comets, even though they're asteroids. Either from things like collisions, so the image is there from Didymos. This is obviously an artificial active asteroid caused by crashing spacecraft into it, or the collection of natural ones there. Things like this are, alerts on those are obviously of interest to say, hey, this thing that we didn't think is active is now active. And then also there's things like disruption events, particularly for comets. They fall apart unexpectedly quite often, and so we want to be able to alert on this comet appears to be no longer one comet. Or a different category of alert is identifying interesting objects that are things like interstellar objects, things that are a short-lived object in terms of when can we observe it, rather than a short-lived phenomena. And so all of these are things that Adler will try and do. Okay, so Adler is not a full broker in itself, much similar to SNAPS in this point. It will work primarily with the UK full stream broker LSST, although it can actually work with lots of different inputs. It doesn't have to work exclusively with this. And as I said, the tools that we're developing will be available for everyone to use independently of whether or not they're working on a feed coming from a broker. So LSST has been running for a while on ZTF and is one of the UK in-kind contributions to LSST, and so it is designed primarily to filter LSST alerts and try and tell you what is this. LSST only cares about the sort of outside the solar system sources, so supernovae, anything else that's gone exploded or changed in a non-moving source. And they tend to just chuck out all of the solar system stuff. And then the idea is that we're going to go and, someone else's junk is your data approach, is take all the stuff they're not interested in and say, well, actually, that is interesting, and we're going to look at it, solar system people. And then within LSST, this is a sort of shot of their webpage. If you go and click on this map of what's going on in the sky and current transient alerts, it will give you an information page that tells you a bit about it, tells you what its designation is, shows you a light curve of recent points, shows you a cutout image of what it looks like and what the template image is, so you can, and the difference. And then within it, it has this thing called Sherlock, which is a sort of automatic classifier that tries to tell you what this alert is. So, for example, if it's a bright dot that appears to be somewhere where there's a galaxy, good chance it's a supernova. It's a bit more complicated than that. It has lots of machine learning. But anyway, they have this predictor called Sherlock. And to stick with the theme, we're called Adler because Irene Adler and Sherlock Holmes. It's not actually an acronym, unlike everything else in solar system, although you can make up one if you want. The neat thing with LSST is it has these watch lists. You can tell it, or categories. You can say, I'm interested in, supernovae with this range of redshift or whatever other property, and then it will alert you when something that matches your criteria pops up. And the idea is to be able to use similar functionality for solar system stuff through Adler. Okay, so what does Adler do? We can look at changing brightness. So one of the things we're looking at is phase curve analysis, so that it will fit multiple different phase curve models. So you can try and compare, does the HG model work better, or does a linear model work better for things like cometary nuclei? And it will take care of things like multi-apparition phase curve effects. So the top one there is from Jamie's recent paper, looking at some asteroid where you see very strong differences in the magnitude between different apparitions, probably because it has some strange shape. And if you just try and fit one phase function to this, you get very confusing results, whereas we'll cope with that. But the idea is, once you've got an idea of what the overall phase function behavior is for a small object, you can then look for outliers and say this brightness is somehow unusual because we understand the underlying brightness model. We'll look at color measurements in a similar way and see whether or not we see anything that's suddenly a different color or is an unusual color. And the other thing that we're doing, as well as looking at the photometric properties, is we're actually looking at the images, because we're interested in things like cometary activity. So we're looking at, does something suddenly have a tail? Does it have a coma? Different models to try and, because different models are sensitive to different sorts of activity. There's different approaches. There's this wedge photometry where you divide up an aperture around an object into different wedges and see whether or not it's brighter in one direction and another. It's good for picking up a comet-like tail. We're also been using this software called Noise Chisel, which is used a lot in extragalactic work, low surface brightness things, looking for how extended is a galaxy. Postdoc Agata Rozek has been investigating using this for cometary activity and looking for low surface brightness things there. So we'll have modules that do this in lots of different ways. Okay. The way that this actually integrates with LASER is following the LSST stream, sending us data during the night, and we're looking at, does this appear to be something new and exciting during the night that we're processing now? And then also we have daytime processing that's looking at the latest catalogs from NPC and saying this is a new object, adding some labels to that are interesting and putting them into our database, and then providing alerts from that. This is just at the nighttime in a little bit more detail. Essentially, what I said before, we're looking for changes from the expected brightness. We're looking for, does it have any extendedness in images? And then we're updating our models based on what we see and based on what other information is coming in. And we're also processing in the daytime. So we have our own database that adds a whole bunch of labels to what you get from the alert streams. That's going to add things that are, flagging potentially interesting things in different ways. Okay, and then just to finish, where are we right now? So we actually started work on this relatively recently, just in the last year. We've got a couple of years of funding developing this, and we've got 2 postdocs working full-time on this at the moment, so the process is quite quick. At the moment, there are various tools already written and are available, and everything's on this GitHub page, so you can go and you can play with code. Everything is open source. And if you've got some feature that you think would be really good for us to work, go to the GitHub and open a ticket and say, hey, what about doing this? This would be great. The idea is this should all be very modular, and we can insert algorithms or whatever from anyone else into this system, and we can work with lots of other different systems. So yeah, if you're interested and you want to work with us, just come and find me or let me know. And I'll stop there. Thanks very much.
Thank you. Any questions?
Hello. Sorry, you mentioned here basically, so the least square phase curve fitting, right? Do you also fit the G1, G2 function? Because for this one, you have limitations for G1 and G2, so you cannot technically use the basic least squares.
Yeah. The idea is to fit, to have lots of alternative models that are being fit for phase functions, for everything, for the also for the detection of activity and images. We're going to have lots of different algorithms that can be run, and then you can look at what you get from different scores in different ways. So, yeah, for some objects, maybe your H1, G2 works best, or HG model, or a linear model, or The idea is yes, we're going to any particular model we can try and fit.
Any other questions? Okay, before we thank the speaker, Colin's also giving a poster on a feedback session of a LSST workshop. It's scheduled for Thursday morning in the poster hall, but we're moving it to here, so it's more of a discussion session. So I will change the program, but if I just be aware that it'll be in this venue and not in the regular poster session. That'll be Thursday morning. Okay, let's thank Colin again. So that's the end of our session. We will have the poster session now, which is only half an hour, but it's combined with the tea session. So please go look at the posters, have a cup of tea, and then be back here in 30 minutes for the final session.
How are you doing? Good to see you. I am good. I was supposed to write an email a long time ago. No, it's okay, but we should. And I just wanted to apologize because my poor student, he got dragged from this project into the millimeter people. I gathered. And so like, they were just, yeah. Really good, yeah. That would be really great. Cool. Very handy. Yeah, no, we should definitely talk. So I'll be around. Yeah. That would be great. Okay, awesome, perfect. Are you co-chair? Chair? Could you please check if my presentation is actually there? It's a good question. Are we able to check on? Very good, yeah. Okay, so we all set. I will be on Zoom. There's an issue, so don't worry about that. I'll be right next to you. So I will also, if there are questions, I'll just point them out to you and you just read them out. Okay. All right. Okay. Yeah. All right. So yeah. Are you guys aware which ones are invited and which ones aren't? Easy on the session. Which? Okay. Great. Okay, so this one is. I'll bold these. I'll bold the ones that are ones that are invited. Do you wanna welcome? No?
Yeah, you can.
Yeah. Go ahead.
Sorry.
Or if you feel, do you want? Yeah. I'll do it. Okay. All right. I hope it's on. Hello? Oh, I guess it is. Okay. Great.
Welcome to the third session of Small Bodies. So I'd like to, first of all, I'd like to thank the organizers, Nick Erasmus and Amanda Sisyphus, and I want to also introduce my co-chair, Hee-Jae Lee from CASI, and I would also like to, our first talk is an invited talk, so that they will have 20 minutes. And that is Milagros Kalajo. He's from Adam Mickiewicz University in Poland. She is, sorry. Okay, thank you.
Hello. Hi, everyone. Thank you for being here. I would also like to start thanking the organizers for giving me this opportunity. And today I'm excited to present you our work titled Large Photometric Database and Application to Asteroid Data from Multispace and Ground-Based Surveys, work that I'm doing with Dagmara, Shemo, and Edita from the Astronomical Observatory Institute in Poland. This one? Great. Thank you. So, as we were talking about in the last talks, nowadays we are experiencing a revolution in astronomical surveys. And thanks to ground-based and space telescope, we have access to millions of thousands of observations of thousands of asteroids in various photometric filters. And this wealth of data can be employed for various purposes, such as examining asteroid phase curves. And these curves offers valuable information about the asteroid surface, characteristics such as the albedo, composition, porosity, roughness, grain size distribution. So our goal is to develop methods and tools for processing asteroid photometry from various sources and to create a comprehensive large-scale asteroid photometric database. And a crucial point in our work is to standardize the data sets so we can write the algorithms and use them for every data set. And these are the databases that we are working with now, Atlas, Gaia, SkyMapper, Sloan Digital Sky Survey, and TESS. And as you can see, they all have observations for many, many asteroids, and together they give us more than 72 million observations. So let me walk you through the different tasks of our project. The first one is the data collation and imputation in the massive photometric database. The second one is the development of the algorithm to compute the phase curves. The task 3 is the application of the method to the data in the massive photometric database. And the task 4 is the analyzing taxonomy and phase reddening, for example. So for the task 1, which is the data collection and imputation in the massive photometric database, we would like to obtain an homogeneous database. And for that, we created a Python implementation that you can find on our GitHub, which is still under construction because we are developing all the algorithms. The first step is reading the original database, and all the databases we are working with are public. And here, for example, for the Atlas data, we use the ROCS package to translate the pack designations to the unpacked designations, because then we will do a query to Horizon system. And well, here I said that while the code maintains a general structure, because it's what we want algorithm that works with every telescope, it incorporates some specific functionalities for each database, and we will see some examples in these steps. So the second step will be the addition of columns requiring per scientific software to obtain spin, shapes, and phase curves. Now we are focusing on phase curves, but we would like to use this database also for other studies such as asteroid modeling, so we try to add relevant information for that too. And in this step, we have some lines of code different between each database because, for example, for Gaia, the time is in epoch UTC, and we want the Julian date in our database. So we have to convert the epoch UTC to Julian date, but then, for example, for Atlas, the original catalog has the mean Julian date. So we need to translate the mean Julian date to Julian date. So that line of the code is different for each database. The third step would be the query to the horizon system. There we provide the ID of the asteroid, the Julian day of the observation, and the observer's location. And again, in this case, for example, for Adler, that has now 4 telescopes operating, we decided to use the terrestrial barycenter as the location. And finally, we obtain a comma-separated file for each object. And the important thing here is that all asteroids from all surveys have a file with the same format, exactly the same format, the same columns, the same name of the columns, also in the same order. And this is a summary of all the databases we are working with now. Here you have the histograms for the number of observations. Here is the phase angle coverage, and here is the distribution in semi-major axis. So as you can see, maybe TESS and Atlas are the ones with more observations per asteroids. Here in Atlas, the mode is 1, but it's because it has a lot of observation of also NRIAG asteroids, but actually it's really, really good. It has many observations per asteroid. The phase angle coverage is quite good for every database, and since we are interested in main belt asteroids for this project, the distribution in semi-major axis is quite good. The task 2 is the development of the algorithm to compute the phase curves, and we are using the AG1, G2 phase function developed by Muinonen and collaborators, but in a multi-opposition fitting approach. So first, we convert the magnitude into flux, and then we divide it into filters if it's necessary. And the fitness process is nonlinear and performed in the flux domain, and the flux is obtained from this equation. Then we split the data in different oppositions using solar elongation information that we downloaded from the last step during the horizon system query. And so finally, for each filter, the data from various oppositions are fitted simultaneously using the same G1 and G2, but different absolute magnitudes per apparition. And here it's important to say that this algorithm works for every database, and it also handles the situation where there's only one apparition available, or, I don't know, for example, when only one filter is available. And now the outliers rejection, but first of all, I would like to do a disclaimer here that from now on, the plots that I will show are made with Atlas data. So now I will use Atlas data to demonstrate our algorithms capabilities. But again, all these algorithms are working for the other telescopes too. So the first aims aim to remove points that lie very far from the mean value of our distribution. And these black points are the ones that didn't pass that step. Then we feed a linear exponential phase function to the data and computed the Ruben mean square residual. And we remove all measurements that differ from the fitted phase function by more than 1.5 RMS. This is a procedure that Hanus and Durek made before, a similar procedure. And the red points are the ones that didn't pass that step. And finally, we apply an additional rejection criterion using the reported maximum amplitude of each asteroid light curve in the light curve database. And of course, maybe one asteroid doesn't have a reported magnitude, so we assign a value of 1 magnitude for that kind of asteroids. And as you can see here, this is the histogram of maximum amplitudes reported in the light curve database, and 95% of the sample has amplitude less than 0.9. And here we calculate the mean magnitude and reject points that deviate from the mean by more than the maximum amplitude. And the green points are the ones that survive all the outliers rejection steps. Now, well, the task 3 is the application of the method to the data in the massive photometric database. Here, to assess the reliability of our results, we compare the derived parameters with those published by Villaver and collaborators this year. They use a very sophisticated approach where they use the ground-based observations to construct the asteroid shapes, and then they compute the phase course with ATLAS data by using that fixed shape. And here, well, we noticed that, we had to use here ATLAS version 1 to consistency. But, here we can see that our results are quite similar to those obtained by Willeber and collaborators, and our method is much simpler because we want to apply it to a very huge amount of data. And here you can see an example of one of our phase curve. The black one is ours, and the red and blue are Willeber's phase curves using two different models. And as you can see, our fitted phase curve is very similar to the model 1. And here you can see the updated phase curve using the data from ATLAS version 2, which is brand new. It came up in May. And here there are two interesting things to notice. First, look how much the G1 parameter changed. And a big difference between these two phase curves is that now we have lots of points in the opposition region. And also here the scale is the same, but the errors in G1 are much bigger than in G2. And that's something that usually happens. Also, you know, the cyan lines are the errors from Willeber, and they are also bigger. So we wanted to study how the parameters G1 and G2 are affected by phase coverage. And here is each part of the phase curve, of the AG1, G2 model. And you can see that G1 is more affected by the opposition region, and the G2 is modeling the linear part. So we performed some simulations of data using an exponential function and the HG function with fixed G1 and then with fixed G2. And as you can see, the G1 parameter is very sensitive to the points in the opposition region, and also its error. But the G2 parameter is not that much affected by phase angle coverage in the opposition region, and its error is always kind of small. So the G1 parameter seems to be highly affected by the density of points in lower phase angles. Then we decided to perform the fitting without the bounds. We can put the bounds that Pentila and collaborator in 2016 set. But the thing is, setting the bounds, the only thing that we achieve is that the points go to the extremes. So this is the G1 and G2 parameters that we obtain. Here are the histogram of the errors. And again, you can see that the G1 errors are much more spread and are bigger than in G2. And from now on, we will also use only the points that falls within the conditions set by Pentila, and also the ones that have errors less than 20% of the parameter. And well, then we would like to analyze taxonomy and phase reddening. And as you can see, the G1 and G2 parameter space using all the taxonomy is kind of mixed, but isolating the two most predominant taxonomic complexes, the separation becomes a little bit more pronounced in the orange and in the cyan filters. Then we analyze the G1 and G2 distribution in orange and cyan for C asteroids and S asteroids. And as you can see, the G2 values for the C asteroids are very, very similar, but the mean G2 value for the S complex is lower in the cyan filter, and that's also noticed by Willeber and collaborators. So we perform also a Kolmogorov-Smirnov test to check, and with 95% of confidence, we can reject the null hypothesis that the distributions are identical in favor of the alternative hypothesis, which is that they are statistically different. And well, finally, we employed the method proposed by Michael and collaborators in 2021 to calculate the spectral slopes using the parameters obtained by fitting the phase curve in cyan and orange band of Atlas. Here, the reduced magnitudes are calculated using the AG1 and G2 parameters that we obtained. And as you can see here, the S slopes are bigger than the C stops, suggesting that, of course, they are more affected by first reddening than the C types, which is expected. And we have developed a comprehensive and homogeneous database that integrates data from Gaia, Atlas, SDSS, SkyMapper, and TESS. Our algorithms for data acquisition, homogenization, outlier rejection, phase curve computation, and taxonomy and phase reddening analysis are fully functional across all the databases. We observe that the behavior of the G1 parameter is particularly sensitive to the coverage of phase angles. And in contrast, the behavior of parameter G2 remains relatively stable regardless of the phase angle coverage. And for future work, of course, we would like to incorporate LSST data. We will continue integrating new data from additional telescopes and updating existing data sets similar to our work with Atlas version 2, because we have everything with Atlas version 1, but now that the version 2 is ready, we are adding all these new points. And for this work, we did not correct for Likert amplitude or geometry. Most of the objects are from the main belt with slowly changing aspects and high number of points. Consequently, the resulting phase curve parameters were averaged over the different oppositions and the number of points. But soon we plan to include these effects in our analysis and compare the results with the result that we already obtained and evaluate the influence of these effects on the parameters. Thank you.
Oh, yeah. Thank you for your question. It's time for, thank you for your presentation. It's time for question. Does anyone have question for him, for she, or? Oh, yeah, okay.
So I just want to ask you, do you extract the photometry yourself, or do you use the survey extracted photometry?
No, we are using for all the databases the photometry already extracted, you know? Yeah. The catalogs that the different telescopes publish is that already with the magnitudes and epochs. Yeah.
Great, thank you.
Any other?
This is awesome, great. Is this clean data set available publicly anyway?
No, the dataset is not public yet because we are still adding data, but I hope it will be soon.
Okay. And then a second question, you had a slide where you're doing a lot of JPL queries.
Yes.
Are you querying every single of those 72 million observations for, phase angles and things? Because that's quite a lot of queries.
Yes, it is quite, it's the slowest part of our project. For example, for the Atlas data, it takes several months, but for the other ones it was quicker. But yes, we divide it because I think that we can query only 50 observations at a time. So it is divided. If the asteroid has less than 50 observations, it goes all together. And if not, we have to divide the data sets in different. But yes, that part is kind of slow.
Okay. Anyone have other questions?
Short question. How about the correlation between the parameters you analyze?
Sorry?
The parameter correlation? Yes.
The correlation between G1 and G2?
Yeah.
What was that? Sorry?
How about how if the two parameters are strong related? Yes, my question.
G1 and G2, yes, they are correlated. Did I put the? I don't remember if I put the correlation here, but yes, they are correlated. Yeah.
thanks again to speaker.
Thank you.
Great talk. So, okay, I think, yeah, okay. Our next speaker is online. Yes. So it is Nick Moskowitz from Lowell Observatory in the US. Nick, you're going to have to share your screen, Nick, to...
Okay. Hello, everyone. Can you hear me?
Oh, yep. And he'll be talking about the Asteroid database. Go ahead.
Okay. Hello, everyone. I assume you can hear me?
Yes.
Okay, great. All right, so I'm going to talk today about the Asteroid database. First of all, thank you to the organizers for giving me a chance to speak with you today. It's been an interesting morning so far, and I'm looking forward to the rest of the talks in this session. For those of you that don't know, Asteroid is a database of minor planet property orbits and properties. The data and associated tools are available at asteroid.lowell.edu. So you can check out that website for anything that piques your interest during the talk here today. I'm going to talk specifically about how Asteroid and some of the functionality that is built into our data system is optimized for growth of the minor planet catalog, as well as sort of complex queries into what we know and don't know about the minor planet catalog. So we have the website that supports a number of different web tools. There are things like Finder Charts, Finder Chart Generator, that has both Aladdin and Skybot plugins. We have a variety of critical lists that are lists of objects updated daily that are in need of data tonight. And so the example I'm showing here is a set of bright objects that have no known physical data. So these are brighter than 17th magnitude, and these objects have no light curves, no colors, no spectra, no albedo. So these might be prime targets for characterization work. And we have long-term observability assessment tools. And so here's one example of that, where we see a variety of observational parameters over several year time span. These can be generated up to 10 years at a time to assess how the observability for certain objects evolves and allows you to define windows for when those objects are accessible based on your capabilities. So those are some of the tools that we have on the website, but I want to focus primarily on the data that we've ingested and created in the database. So Asteroid has a long history dating back with tendrils going back into the 1970s. It became fully publicly available in the 1990s. And again, all the data and tools are available on the website asteroid.lowell.edu. If you're interested in some of the details of the data system, you can check out this open source or open access paper that we published in 2022. Asteroid is an actively curated catalog of orbits for all known asteroids in the solar system, almost 1.4 million objects at this point. Augmented that catalog of orbits with dynamical and physical properties. So these are all being stored in one place to enable complex queries. And that's really the sort of take-home point for much of the talk here is we've created a data system for fast, complex queries that is ready for future growth from upcoming surveys like LSST and NEOSurveyor and SphereX and others. And so I'm going to spend much of the rest of this talk talking about the types of queries we can enable based on the physical properties and orbital and dynamical properties that are available in the database. So I'm going to give a sort of quick overview of some of the physical properties that are stored in Asteroid. These are compiled from a wide variety of sources. In the figure here on the left, we can see examples of albedos and diameters from NEOWISE. We've ingested these properties from just about every major survey of this nature. We have almost 200,000, 192,000 albedo diameter measurements ingested into the database. We have ingested a large number of broadband colors across various filter sets, Johnson-Cousins UBVRI, Sloan UGRIZ, and JHK and near infrared. We have nearly 1 million color observations in the database. We have spectral taxonomic classifications from a variety of different surveys. Nearly or over 100,000 taxonomic assignments are stored in the database. And we have essentially a regular sync with the asteroid light curve database, which contains 34,000 light curve properties. And so all of these are updated when needed and are available within the Asteroid database. We also have a variety of dynamical properties available. So for every object in the database, we assign a dynamical type, which is kind of summarized in this table over on the right here. From near-Earth object dynamical classes out to the TNOs. We have a variety of computed properties, including Jovian-Tisserand parameter. For NEOs, we compute a delta V. We have planetary moids computed for every object and all the major planets. We have an orbit quality parameter as well. In addition to those dynamical properties, for NEOs, we assign escape route probabilities for the 7 major escape routes in the main belt that we think feed the NEO population. This is from the Granvik et al. 2018 medium resolution model. And so we have these probabilities assigned to every NEO in the database. And we also have dynamical family membership information. This is from integrations by David Nesvorny in 2015. We have about 140,000 objects with dynamical family membership assigned. So that's a quick overview of some of the data that are in the database, but how do users get at that? And that's what I'm going to spend the rest of the talk going over here. We have multiple modes of access to the data. In addition to the web tools, we have API that's been developed, and there's documentation, this QR code in the upper right-hand corner there if you're interested in API access. I'm not going to talk too much about that, but instead focus on the web-based query builder. And so this is a web-based query tool that the user can define different filters to set up a query. And so I show the full range of available filters for issuing these queries here. This is pulled directly from the query website. And so you can see you can define queries on H magnitudes and dynamical types, and a long range of parameters over here on the right. And so I'm going to step through those really quickly. We have orbital properties, the Keplerian elements, non-gravitational terms, moids, delta Vs. We have observability parameters, so dates, Vmags, dex, elongations, etc. We have that dynamical family membership. We have major families like the Pallas family, Juno, Vesta, Flora families, and 114 other collisional families in the main belt and Trojan regions. Period and amplitudes for the light curves. Albedo, diameter, and Needham eta when that is used to fit the data to derive albedos and diameters. We have 13 different taxonomic systems that have been ingested along with the associated types for each of those systems. Again, we have multiple broadband color systems ingested and actual measured colors. And then again, we have the NEO escape route probabilities for the 7 major escape routes from the main belt. So each of those parameters are available within this sort of web-based query builder. And so I want to give just a couple brief examples here of the types of queries that one can issue with this tool. So this would be sort of for the observers in the audience. Maybe you're interested in small NEAs on low delta V orbits, low Earth moid, observable tonight from the south. And so in a relatively few number of clicks, you can toggle on different parameters in the web interface. And so you can see at the top there, we've toggled on H magnitude to search between 20 and 35. We're looking at low delta V from 0 to 6 kilometers per second. We're looking at low moid objects with the Earth between 0 and 0.05 AU. And then we define observability as brighter than 20th magnitude and solar elongations greater than 60. And then again, observable in the south, so declinations less than 30. So we issue that query. Takes about half a second to run, and we find there's only 3 objects tonight that meet those parameters. We can follow up on those 3 objects with our Ask Info page, where you have a RESTful URL interface or RESTful URL capability that allows you to issue queries to that tool. And we can find different things that are known and not known about these objects. So for one of these objects, we don't know its rotation period yet, and for the other 2, we do know rotation periods, but we don't know albedo. One last example here, maybe you're not so much interested in observability, but say compiled properties across different data sets. And so in this example, we'll look at the reflectance properties, albedo, and spectral type of Trojans and the Euripides family. And so again, over on the left here, we select dynamical type equal to Jovian Trojan, dynamical family membership. We choose a wide range of albedos to capture everything, and then we're selecting any spectral taxonomy. We issue that query, and it runs in about 1.5 seconds, and we can see the results of the query parameters there. For every query that's run, a URL is generated, which provides a direct link to a JSON version of the query results. And so just to finish up here, I realize I'm kind of long on time. So Asteroid is this comprehensive system of minor planet data that we've built up. It's both API and web accessible. It's been optimized for these multi-parameter complex queries, which is really important in this era of big data. There's a lot of ongoing work here. And I'll just finish by saying that Asteroid is meant to be a community resource, and we always welcome feedback. And you can get us at this address, asteroid.lowell.edu. Thank you very much.
Thank you for the presentation. Unfortunately, we don't have any question for him. If anyone have question, maybe we can discuss with him by email. Yeah. Okay. Next move.
Thank you. So the next presenter will be Tobias Hoffmann from Karl von Ossetsky, University of Oldenburg, Germany, discussing defocus.
Yeah, with my presentation, good afternoon, I want to put the focus of this focus meeting on the defocus, which is a statistics-based correction algorithm for asteroid photometry. So a nice follow-up on the first presentation of this session, where we have a look at all like the asteroid photometry available basically from all observatories. Basically, we use all the MPC observations that are available from all telescopes around the world. And if we see, if we have a look there, then it's quite diverse actually. We have high errors there, like one are intrinsic based to the color, different colored offsets we have, different color bands that are measured from blue to red, infrared, and so on. But there are also quite high measuring uncertainties, as you can see in the right plot here. And it's quite diverse, which leads then, of course, to a quite high accuracy in the estimation of the size and the age parameter and so on, which is, of course, of high importance for like characterization and planetary defense purposes. And what we want to do is we want to debias these errors, like look if there are systematic errors in these data sets actually, which is quite complicated. And if so, we first look at there are current color corrections that are in place by Minor Planet Center. We look if there is a statistical deviation from these corrections, basically, not only from the color perspective, but also for the individual observatories or different catalogs that were used for the derivation. And with that, we want to try to develop a new systematic correction algorithm to better get better fittings of the HG phase function, basically. I don't want to get too much detail here. Basically, what we use is a database reference of like 1,000 asteroids by the observer Peter Brabeck. We calculate the residuals out of the observations and do some statistical analysis of this. First, for the different color bands that were used, then also for the photometric catalogs that have been used to derive the photometry, and then also for the observatory itself, basically. And if we look at the color corrections first, if we compare this to the current, these are the current color corrections that are in place by MPC, also in UCC from ESA, and we correct like what is the average offset we have here in the different color channels. We see it's quite good agreement for like the modern bands that are used by major surveys like the Adler or the or the Sloan bands are also quite good agreement, which you can see in this column here, and then the difference in the back there. Some majorly used bands like the V band, of course, the red band and the Gaia G bands are also quite, at least some good. There's some slight deviations, but it's not too accurate. We have some where we do not have too many observations. We have like certain statistics, but especially there's some for the Panzer's W band. Like there's like nearly signs change basically on what we get, like color correction in magnitudes given. So we propose there is no other correction needed for this filter used with this band. And if we look also at the different catalogs, we see it's quite diverse. Basically, old catalogs that are used here in the V band, they have like specific other biases compared to newer ones. So it's not easy to say, oh, this is the color correction for this one. And we did basically an analysis out of this and put a correction algorithm. This is like in an iterative approach, more or less. We start with the current corrections that are in place by ESA, by NEOCC, and then we apply the new results that we get with our color band analysis. We do there a statistical test in order to only have those corrections that are really statistically deviating from the previous ones and that are really confident based on a statistical test with a certain certainty level. And then we apply these rules, and then we go to the next step. We also append the catalog corrections that are based on the specific band, and then also add the different observations to it. So there are different categories there where we have more specific rules then. And what we get out, we have like this one parameter open where we can say what confidence level we would like to have. And we compare then this for like part of this data source, like 60% for validation, and like how are the RMS improving of the photometry of the light of the phase curves actually compared to the current corrections. If we have like certainty level 0, then it's basically we apply all corrections, which is not the best, as they are like really not certain because there are not too many observations in these. But we have found there a sweet spot. If we increase the certainty level, we get a reduction of up to 36% of the RMS. If we increase further the certainty level, we reject kind of some corrections by specific observatories that can play some meaningful role there. So that's why it's then decreasing slightly again. If we increase the certainty level, basically. Yeah. And for this value of certainty level of 90%, we get like the sweet spot there with a reduction of 36%. Exactly. And what we then did also is we tried to use the new correction compared to the previous ones to predict the H or the absolute magnitudes, the H parameter then, and we found like quite good agreement, or better agreement than previously. We are overall decreasing the overall RMS for all phase curves basically by quite some extent compared to previous corrections. So we propose to use like some new correction algorithm for the specific observatories. So that would be my take-home message basically for you. Photometry of asteroids does matter, and yeah, we can do some data science to derive some promising results. Of course, this will be better if it is quite small reference database. We usually use if we have like bigger data sources, will be of course improved again. And there is also specific deviations from the individual observers. Those need to know about this more. There are quite like really some outliers there, which is really interesting. And I hope we can get into some discussion with that. Either contact us here or me here at the IAU GA or via mail, and we will have from ESA a specific workshop with the European Union on the size determination of potentially hazardous asteroids in November in Darmstadt, where we'll also discuss this topic of the different color and devising of photometry more specifically, as this is crucial for this part, for the potentially hazardous asteroid, of course. So with that, I want to thank you very much for listening.
Thank you for the nice talk. Does anyone have a question?
for your talk. So I had an opportunity to work a little bit with test data, and I looked at the light curves that they published, and I ran my simulations as well, my code. So I found out that more than 50% of the data that they published were actually not accurate, and so you cannot use them basically. So my question would be, because I guess this can change your statistics, right, and your biases. So did you clear out some of this kind of bad light curves when you did your bias statistics? Or something?
Yeah, there are two things. There's some systematical bias that is there, but which we see also for tests actually, and then also like the deviation is quite high for tests. We saw that too. We didn't include this in this whole thing. It's planned for future works to have like a fitting or like a weighting scheme to have like how to weight which observations based on the deviations they have. That's not currently in place. That would be like an additional thing to do, but we have that in mind. Yeah.
Okay, we have more time for one short question. Does anyone have a short question? Oh, okay, thanks again.
Okay, our next speaker is Josef Durek from Charles University, Prague, Czechia, and we'll be talking on combining photometric data sets for asteroid light curves.
Good afternoon. This talk is related to previous talks. It's also related to asteroid databases and asteroid photometry, and I will try to convince you that combining photometric data sets from everything that is available is an efficient way how to reconstruct asteroid models. Asteroid photometry can be used, as I said, to reconstruct shape models of asteroids together with their spin information, the period and spin axis direction. And the process is called light curve inversion, and all we need basically is sufficient number of photometric measurements that cover sufficiently wide range of observing geometries. And by this method, more than 10,000 asteroid models have been derived, mainly from classical light curves and also from sparse in time photometry. Sparse in time means it was asteroid photometry term used in previous talks. And this sparse in time photometry comes mainly from Gaia, DR3, and Atlas surveys. So that's what has been done, and now we are basically waiting for future surveys, future release Gaia DR4 and LSST observations. But meanwhile, we can do more. We can include all other major surveys like Catalina, ZTF, Pan-STARRS, and TESS, for example, or others. And combining everything that is available is the most efficient way how to produce asteroid models. So here is an example how it works. A typical asteroid for which this inversion was successful, 5,000 IAU. So here is the photometry from 8 the largest observatories or surveys. This includes 10 data sets because some observatories observing 2 or more filters. They are listed here. They are color-coded, and the data cover about 10 years, and there are 1,200 individual points in 7 operations. And you can plot the same data, brightness reduced to unit distance versus the solar phase angle. So you see the phase curve, but there is noise in the data, and there are effects caused by the shape and by the geometry. And there are also shifts between observatories due to some systematic effects and different filters. And after the inversion, when we have a unique model, the shape model and the spin state model, what remains is a kind of mean phase curve that is free of any shape and geometry effects. So this is the clear phase curve. And this is the result of the inversion for this asteroid two possible shape models with two different spin axis orientations, a unique determination of the rotation period, and we also have the color indices, the shifts between those different observatories or filters. And as I said, the phase curve that is clean of any shape effects. So this was just one example, and we can do this for basically every asteroid for which some photometry is available. So we did this for every numbered asteroid and run this light curve inversion, but due to low number of points and high noise in the data, we were successful only in these cases, so we were able to derive slightly more than 20,000 asteroid models, where the number of observations was sufficient. So here is the histogram of measurements per asteroid. So you see that most asteroids have only tens or a few hundreds of observations over a couple of years, which is usually not sufficient to derive a unique model. So to be successful, we need, in this case, hundreds up to thousands of individual observations. And the purpose why we are doing this is, of course, to study the distribution of these physical parameters inside the asteroid population. So the more models we have, the better. And then if we have, like in this case, 20,000 plus models, we can start to look at the distribution of, for example, periods and spins inside the population. So this is the famous plot, rotation period versus size. So the rotation period is known for tens of thousands of asteroids, but in this case, we also have information about the shape elongation, which is color-coded here. So the blue points are basically spheroidal asteroids that can come very close to the spin barrier. And those that are more elongated are shifted towards longer rotation periods. Then we can look at the distribution of spins inside the main belt, and we see nicely that we see the role or effect of the Yarkovsky drift, because blue now are prograde rotators, red are retrograde rotators, and those asteroids that are prograde, they are moving on long time scales towards higher semi-major axis. So the blue points are shifting to the right, and they cannot cross the mean motion resonances. They are scattered, so they are missing on the right-hand side of those mean motion resonances, and vice versa. The red points, they move to the left, and that's why they are on the right-hand side, and they are missing, for example, here, and also here in the outer main belt. The same Yarkovsky effect works also inside asteroid families. So here is one example of asteroid family Themis, where again, so this is semi-major axis. This is H magnitude, which means the small asteroids are on the top, and this is the largest ones inside the family. And we see again that prograde are to the right of the center and retrograde are to the left. And moreover, we can see also clustering of spins inside some of the families, like in this case of family NEOMIR. So this is the distribution of spin axis directions in ecliptic coordinates for the members of the family for which we know the spin axis orientation. And the first thing you see is clustering towards ecliptic poles. So these are poles that are close to the ecliptic are less frequent. And in some families we see this kind of group that are progradely rotating asteroids that are trapped in a spin orbit resonances in so-called Slivan states. And they are greenish here, which means they have also similar rotation period. So, as I said, the aim is to have as many asteroid models as possible to see pictures like this. And the next big change will come with Ruben Observatory LSST survey. Here are some numbers expected from LSST that are related to solar system science. So the number of asteroids, known asteroids, and also of asteroid observations will increase dramatically. So we expect a dramatic increase in the number of asteroid models. But to get those numbers, we basically need to wait a couple of years or the whole 10 years. But meanwhile, we can use what's already available. So here is the distribution of maximum brightness for all those asteroids that were processed by us. And even if LSST will observe much fainter asteroids for which we do not know any photometry now, for all these, we have some photometry from current surveys. And this photometry can be immediately combined with whatever comes from LSST during the first months, years. So this is kind of in advance follow-up, because we already have follow-up for LSST now, and we can combine photometry from LSST with what is available now. And that should be an efficient way how to produce quickly or efficiently new asteroid models. That's all. Thank you for your attention.
Thank you for the very nice presentation. Unfortunately, we don't have any time for question. If anyone have question, you can go end of this session. Okay, let's move to, thanks again to presenter.
Okay, so our next speaker is Alex Gibbs from the University of Arizona's Catalina Sky Survey, USA. And we'll be talking about prioritizing and coordinating NEO follow-up with NEO Fixer.
Thank you. Let me know if you have trouble hearing me.
We can hear you.
As mentioned, I'm Alex Gibbs from the Catalina Sky Survey, and talking about prioritizing and coordinating NEO follow-up with NEO Fixer in the area of large discovery surveys. Let me get the chat window up just in case there's any volume issues or other issues. Just let me know. All right, so let's go on. So what's the issue? Well, as we've already been talking about, we expect a lot more discoveries in the coming years. That means there'll be an unwieldy list of targets to go through in order to try to find those that are most in need of follow-up. There'll also be more ARC extensions as the catalog gets larger very rapidly. There's limitations to self-follow-up, and the current resources, follow-up resources, aren't expected to increase all that much. So that leads to a problem of not enough resources. So what can we do? Well, we need to make follow-up more efficient and beneficial, but also easier. And that's exactly what we've designed NeoFixer to help with, not only for the upcoming problem, but in addition to help our own follow-up situation with the discoveries that have been coming out from us and Pan-STARRS and Atlas and others. So let's see. So how does NeoFixer help with this? Well, we prioritize objects, especially in terms of planetary defense. We generate customized target lists that are customized for each telescope so that they can maximize the benefit of their own observations. We aim to improve coordination between sites by making it easy to report their status of observations, whether they are expecting to observe something, whether they have, whether it's been reported or not, whether they found it or didn't find it. Also to aid in automation by providing an API that's relatively easy to use in terms of getting a list of targets, getting observation parameters, exposure times, and for reporting the activity as mentioned. So let's talk about each of those categories that NeoFixer handles individually. So first is prioritizing targets. So NeoFixer generates a NeoFixer score that consists of these different subscores. The first one is the importance of the object, and especially in terms of planetary defense. The benefit of observing the object, how much can we improve the orbit? The urgency in observing the object, is it becoming easier or harder to observe for a particular site? So these last ones are customized per site. The cost of observing the object at the site, and then the interest by others around in the community in the object, whether they're interested in, whether they're planning to observe the object or have observed the object, whether they're about to report their observations or not. So let's go on. So those NeoFixer scores are calculated per site and then generated for each object and then converted into a ranked target list. As mentioned, it is for a particular site. Targets, or the scores, vary from site to site because not every object is available or observable by all objects, all sites, that is. Note that the score is also converted into a text priority level. Basically 9 and above is critical, 8 and above is very high, etc. So we generate the prioritized target list per site, and there's customizations to that I'll go over. So one of the things, let me go back. You may be wondering, well, why a certain object is scored a certain way? And there is information available on the website. If you click on object, you can get per object information. You can get a score breakdown, which I'm not going to have enough time to go into, but that gives you an idea of why a certain object is the way it is. You start with the basic sub-scores, and you can see that one of the scores is much higher. So in this case, the object is very urgent because it's becoming unobservable. So that's why it gets scored so high. There's also a plot that shows the scores over time to see that you can use to see on which particular night an object may be best to observe. In this case, this is the one I was saying it's becoming unobservable as the uncertainty increases. So you got to get it tonight, essentially. So the next category was customization. As I mentioned, the target lists are customized for your telescope. So you need to, if you register and provide your telescope's details, then the targets are filtered to the ones that you can actually observe. And they're ranked according to your capabilities and to maximize the benefit of your particular telescope's observations. But you can choose which objects you want to observe. It is a target recommendation list. And also, I meant to point out that it's not a scheduled list. If we go back here, the objects are not listed by the order in which you should observe them. Although you might be able to do that by, listing them by RA, for example. You can sort the table here. But in any case, it's not meant to be a queue manager of any sort. It's just a list of the targets. We have a separate queue manager that we use at CSS, for example. So the customization also extends to customized ephemerides for your telescope that include things like the exposure time. You can also customize the target list with filters, such as the ones listed here on the web page, and then you can build up a query essentially for the API, and if you click here and copy the link, you can then feed that to your API. That way, it makes it easy to, on the web page, generate a customized target list or a type of target list, and then use that API link later on. So something that's new at NeoFixer is the activity page. We've been accepting status updates for a long time about the object's status, and that's shown here in white, but we haven't had a good summary page that shows all the activity from all the sites within the last 12 hours. So now we have this. It's available from the main website. It's brand new. This is the first time it's been mentioned in public, but allows you to get a summary of what everybody's up to. So there's some customizations. You can change the columns, you can change the telescope visibility, etc. But for the status reporting to work, you need to, for the coordination to work, people need to report the status of their objects, which they can do easily on the web page itself with these drop downs or with the API. And that brings us to the automation. There's documentation on the web page from the API link that gives you information about how to use the API to help automate your system. So CSS uses NeoFixer in this way. There's typically from the API, and then we get a list of targets and that are filtered down depending on our observing conditions, etc. We send those to the queue, which also uses the API to get the ephemerides and exposure times. We then continuously throughout the night auto-update our priorities of the targets so that if somebody else observes a target, it'll drop off of our queue, for example. And then we're automatically reporting the status of the objects as they move through our pipeline and what we're doing with the objects so that others hopefully won't re-observe the same object. So this shows how the use of NeoFixer has changed our results, our follow-up results at Catalina. There's an increased benefit per submission over the years. We've also, especially last year, reduced the number of observations, number of follow-up observations that we sent in, while the benefit per tracklet has gone up, mainly because we were emphasizing following up fainter objects, but more valuable objects. So they take longer, so we get less of them, but overall the value goes up. In 2022 at VO6, we kind of hesitated to do that, but obviously once we started doing that, the value of our observations at VO6 went up. So in summary, NeoFixer already allows the community to handle and manage the observations, the follow-up of the 35,000 plus NEOs that are already known, and will continue to do aid as we increase the discovery rate from other surveys. The main ways are by prioritizing targets to help the observer save time in figuring out what targets to observe, but also in preventing objects from being overlooked, and customizing target lists for each site so that they can maximize the benefit of their observations, but also providing a way to coordinate in a semi-automated way by just reporting the status of your observations either through the API or on the website, so that it'll reduce over-observing in favor of getting other targets, and by making it easier to hopefully automate your systems and improve efficiency. So with that, I'm done, and thank you very much.
Thank you for your presentation. We have one question from, anyone have? Okay.
I just have a quick question, Alex. This is Gersbauer from University of Maryland. Hi. I know, does this yet incorporate comets and cometary objects?
Yeah, yes, we do have comets included. They aren't treated any differently than NEOs, though, so they're not promoted because of being cometary, at least not yet.
Great, thank you. All right, let's thank our speaker again. And our next speaker is Siegfried Egel from the University of Illinois, Champaign-Urbana, USA, and he will be discussing Ruben rocks.
Thank you very much, James, and thanks everybody for the invitation to speak here. So my name is Siegfried Egel, and I think if we would make a word cloud of today's talks, you would have automation and where's the Ruben LSST like really pop out. And this is one more piece of the puzzle that we think could be really useful in that context, namely how to provide the community with some easy access to the dynamical histories of near-Earth objects. Now, we've heard a lot about the LSST. I really thank Joseph for giving a nice summary of how many solar system objects we really expect this thing to discover. Joko also pointed out today that there is sort of two cadences that are really, really interesting. The one is the alert cadence, where you can really figure out how many objects change on a very, very rapid time scale so that you can go ahead and follow up. And then there's sort of the next tier, which is discovery of new objects, where you really have no idea what this thing looks like before, and 24 hours afterwards, like if you go through the NPC, hopefully you'll find a list of updated objects there. Most of them will hopefully be also sort of linked in a way that they can be confirmed fairly easily. Now, of these 100,000 or so near-Earth objects that we expect LSST to discover, I think we've heard in the past couple of talks that prioritization for follow-up is some of the key point that everybody is going to be really interested in. So if you have 100 NEOs per night or so, like which ones are you going to dedicate your resources to follow up? And there is basically a bunch of ways you could look at this. First of all is the planetary defense aspect. You know, does this potential NEO impact the Earth? But there's also other aspects, like for instance, you know, is this going to be an active thing? What kind of materials constitute this sort of asteroid? And wouldn't it be nice if, with all the parameters that you get from the LSST database and the alert database, you could also directly access the dynamical history of those NEOs? For instance, you know, where does this come from? Where are the dynamical escape routes? What are the residence times? Did this asteroid spend, you know, like a million years or so far away from the sun? Did it just pass close to the sun and come back out? So this is all the things that we hope to fulfill, we hope to achieve and provide to the community with the Ruben Rocks API. And what that is it's an NSF-funded API that really tries to dig into the current NEO models that people spend quite a lot of time and brain power to develop. If you don't know what a NEO model is, it's basically a huge data set that has been created through forward simulations where people try to figure out like what is the actual population of near-Earth asteroids that we are predicting to be out there. And for this, you have to debias all the observations, you have to create models. So there's going to be a huge effort has been spent to really try to understand what those look like. And there is a lot of information contained in those models. The only problem is like, how do you access that? So let's assume, you have no idea about those. How would you go about and find out the dynamical history of the object that you're interested in? Well, you would go, for instance, to NEOCP if you go for objects that haven't been confirmed yet, and you'd have some orbital elements. You'd take the uncertainty of those orbital elements. You'd launch 1 million clones. You'd propagate them, like, I don't know, 100 million years or so in the past, whatever lifetime you think it is. And then you would try to figure out, okay, where does this come from and so on. But then, like, propagating stuff into the past is really tricky. So plus, like, you burn a lot of CPU power. And if you do that for every unconfirmed object, you quickly run into trouble, I think, with whoever funds you. And so there's a smarter way of doing this, namely to use those NEO models and basically try to extract information of where stuff comes from based on those models. Now, the second way you could do this is you download all those models and try to do this yourself. And yes, probably most of us could do this in a bunch of hours, but then everybody's really busy, so why would you ever do that? The third and also very comfortable and convenient method has just been presented by Nick. You go to AstroOrb for any NEOs that are known. You can actually go to AstroOrb and extract information of the source regions, for instance, in a very nice and easy API manner. Now, if you want to use NEOSP, for instance, that starts to become a bit more complicated. And so this API is really there to basically provide you with the means to kind of do this yourself. Even if you want to have like a new discovered object with huge orbit uncertainties, you can simply ping this API. It's reasonably well documented, and then you will get the dynamical histories, not only where the stuff is supposed to come from, what the probabilities are, it comes from U6 and so on, but also what are the residence times, what are the likely dynamical fates. And so this is a really, really nice, I think, addition to the swath of APIs and problems that we already had heard of today. And for those of you who don't really like Python or any sort of API interface, there's also a clickable thing, a nice website. So please do check it out. We tried to launch an alpha version just in time for this meeting. Here, for instance, like you can put in like some symmetry, eccentricity, and inclination, and we currently use Sarah Greenstreet's model to get you then some sort of nice plots that you can zoom in, where you can look at the neighborhood of where the stuff comes from. It's not only like basically, taking your orbit, you can really look at around and see what the likelihoods are. You can make your own probabilities and statistics of if your orbit uncertainties are large, if this is an interesting object for you. And, you have like several different slices through that data set that you can visualize and really like zoom in and play with. This is not everything there's going to be. So we really just started working on this, and hopefully by the launch of LSST, which I'm pretty sure is going to be in a year, hopefully, I'll be optimistic there, we should have this figured out with every current NEO model there is, David Ness-Warren's model, Mikkel's model, Sarah's model, with a lot of additional info that hopefully will all be useful, not only for people who are really interested in NEOs, but also for alert brokers and so on. So hopefully that's going to be useful. Thank you very much. That's all on my end.
Thank you for the nice talk. Does anyone have questions to him? No question? Oh, yes.
Yeah, really nice. Any thoughts of extending it to other solar system populations or dynamics outside of the NEOs?
We don't get paid for that yet, but it's a very good idea. So I think this is going to be useful for a lot of things, especially, Adler may be also something that may be interested in this. But yeah, very good idea. Especially comets could be something to look into.
Okay. Any more questions? Okay. Thanks again to speaker.
Thanks.
Okay, our next speaker is Dmitry Vavilov from IMCCE, Observatoire de Paris, France. And we'll be talking about near-Earth asteroid follow-up and precovery.
Yes, hello everybody. I'm Dmitry. I'm currently a postdoc at Paris Observatory. I'm glad to present our work about using the uncertainty analysis for follow-up and precovery asteroids. So pointer is this one. Okay. So if you look at the observations of asteroids, generally they look like this. So it's either a moving point, or if it's an old observation, for example, then there's going to be this kind of trail that you see. And the problem is that just with this data, it's impossible to get the orbit. So you either need several of these ones in several days, or you can link this observation to already discovered object and use it. But so if it's not a newly discovered asteroid, it's not a new one, then this one would not be enough to compute the orbit, but we can identify it to what asteroid this observation belongs to and use it. So this is what I'm going to talk today, and our method, how we're going to link the observation with the already discovered asteroids. It's also the same approach can be applied for precovery of asteroids, that is finding old observations of the known objects, and for follow-up as well, same but for future. So what is the problem actually we have? Because for a bunch of asteroids, especially newly discovered asteroids or unnumbered asteroids, we don't know the precise orbits. So we have some uncertainty, let's say, in the velocity of the object. And so after some time, this uncertainty of the velocity multiplied by time gives you the uncertainty of the position of the asteroid. So you think that your nominal position of the asteroid is here, but it also can be here, or it also can be here. And then you see some observation, and it actually belongs to this position of the object, and the nominal can be really, really far from the actual observation, let's say 10 degrees. And that's why it's really difficult to link them if you just integrate the orbit and see where the object is. So for this, we proposed using this method. It's a modification of the partial banana mapping method. And the idea is the following. So you have an observation, and then you want to check if this observation can belong to this object. So you take the orbit of this object, integrate it up to the time of the observation, and then with variational equations. So we have the covariance matrix, and then you use the covariance matrix in orbital elements, and it will approximately give you this uncertainty region, like where the object can be. And so this uncertainty region is going to be curved, mostly stretched along the osculating orbit, and actually also not symmetric, because the closer you are to the perihelion, the closer the asteroid is to the perihelion, the faster it's moving. So that's why it's also not symmetric. So, as I said, we use the Gaussian distribution of orbital elements. The problem is that it's orbital elements, 6 of them. We don't really know how it's distributed in the 3D space. And so to deal with this, we take the main line of this curved uncertainty region and just take several virtual asteroids on them, so several points. Here in this work, we use 51 virtual asteroids on the 5 sigma interval. And then each of them would just map onto the celestial sphere and get the coordinates, and this is how we get the uncertainty region for the position of this object on the sphere. So we use this one right now for pre-covering of asteroids on the photographic plates, which are available at Paris Observatory. So we have this bunch of them from different observatories, copies of Palomar as well, and the plates are actually quite big. So they're 6 degrees by 6 degrees, so a little bit larger. And yeah, so there could be asteroids there, known asteroids, but we don't want to look at each of the plates and look for some kind of a trails. No, it's that would be a hell. So that's why we apply this method. And the way how we do it is, so for each of the asteroid and each of the photographic plate, we compute these 51 possible astrometric positions, and then look if the asteroid can be on this plate. And then compute the probability that it's on the plate, estimate the visual magnitude, also the length of the trail, how it should look like, because if it's too small, then we would not be able to distinguish it from a star. But if it's too big, then probably it's going to be too faint. And also the size of this uncertainty region. It's also very important, because first we want to select the plates where we can find the asteroid, so we have some high probability that the asteroid is on the plate. Of course, they should be bright enough in order to find them, to see them. And also, we don't want the asteroids with the uncertainty region which is too small, because if the uncertainty region is too small, that means that the orbit is already good. Why should we take a lot of time to get the observation if we don't improve significantly the orbit? This is probably the most important slide of my presentation. This is how the method works. So here in the purple box, you see it's the photographic plate. This orange dot, it's the nominal position of this object, of this asteroid, 2015 UM67. You see that it's outside from the photographic plate, actually quite far from this one. So if you use conventional tools like Skybot, so it will tell you just that, okay, the object is not on the plate, and that's it. But if you look at the these blue dots, which actually these 51 points that we took, so you see that some of them are actually on the plate. And so it means that there is a probability that the object is on the plate, could be found. And the red dot here is the actual observation. So you see the method worked pretty nice. So you can find this observation. And so if we had this observation before, that we can just link it to this object, because we see that, yes, it is there. Just to clarify, this green line, this is the uncertainty region, the way if you just take the covariance matrix in right ascension and declination and map it here. So you see that it's actually quite different from what we expect to be reality. And so the point is that just taking the covariance matrix is not enough to estimate the uncertainty region of the asteroid. This one is just a zoomed picture of this of the previous one. So the red one is the observation, how we saw it. The blue Here it's our prediction of where the observation should start, and this lines is our prediction how the observation should look like. So you see we have a really nice agreement with this. Okay, so the conclusion, so yes, we have a new method how to link observations with already discovered asteroids. This technique is quite fast, so it's pretty applicable to large data sets, and yes, the method works it's more reliable than some of the tools available right now. So thank you for your attention.
Thanks for the nice talk. Does anyone have questions? Oh, yes, okay.
So was this the only object that you could recover, or, I mean, how many plates did you look at? Could you recover more asteroids than just this single one?
Yes, sure, of course. It takes time first, but this one was just an example how it works, because I think it perfectly explains the advantages of our approach. Yes, but yeah, we're doing it in its process. So, but it takes time, yes, because we need to take the plate, move it, then find it, and scan it, and do it. So it actually takes a lot of time to process.
Okay, thanks again to the speaker.
Okay, our final speaker of the day is Kai Tang from Shanghai Astronomical Observatory, Chinese Academy of Sciences. And we'll be talking about error analysis for rotating drift scan change coupled device observations.
Good afternoon, everyone. I'm Kai from Shanghai Astronomical Observatory. Today, I will talk about the error analysis for the rotating drift scan method to observe the near-Earth asteroid. Oh. No? Oh, okay. Okay, my report contains 4 parts. First is the introduction. For follow-up observations, asteroids are only bright enough to be detectable when they are close to Earth, but their apparent speed are usually high when they pass by the Earth. There shows an example that the relationship between the distance to Earth and the apparent velocity for this asteroid, and you can see this very high apparent velocity will cause trouble for follow-up observations. And here, the rotating drift scan method introduced here is special for observing fast-moving asteroid, faint asteroid, which means that long exposure is needed, and with small aperture telescope. This is the parameters of telescope we use. One is in Lishan, China, and another in Mykolaiv, Ukraine. And they are all 14 centimeter small aperture telescope, and use the same CCD camera. What is the rotating drift scan technique? We all know that when we take a shoot of stars with a long exposure, we can get the star trails. But with the drift scan method, we can get the round image of the stars. But unlike the stars have the fixed apparent velocities, asteroids have different moving directions and apparent velocities. So we need to rotate the camera and adjust the charge transferring speed to let the drift scan method can also be used for observe the asteroid. this frame is you can see that we use this RDS technique to get the round image of the asteroid, and due to the long exposure time, the image of stars becomes the lines. It will also cause trouble for position measurement. So we introduce a special astrometric reduction to obtain the coordinate of the object. Two frames of fused stars are needed, one before and one after the frame of asteroid, and the plate model of the second frame is determined using the reference stars from the first and the third frame. You can see the red dot is the plate model of the second frame, and the green one is the plate model of the first reference stars. And we use linear interpolation to get that. And the telescope must keep stationary during the whole observation process. Now, next is about the error analysis of this RDS astrometry. We use the RDS observations from the telescope in Lishan from 2029 to 2023, and the telescope in Mykolaiv from 2011 to 2024. There gives the details about our observations, and it includes about 11,000 positions of nearly 500 asteroids. We determined all the asteroid orbit with all observations from all over the world and calculate the observation residuals. And we use statistic distribution of the root mean square calculated per set, per asteroid, and per net to scale the observation uncertainty. To estimate the RDS ability of observing faint near asteroid, we calculate the mean and standard deviation changes of root mean square residuals with magnitude in rate accession and declination for multi-apparition asteroid. And on the left figure, it's RDS observations. The uncertainty increased slightly with decreasing magnitude. The limited magnitude of our telescope is 18, and to observe such faint object, more integration time is needed. But RDS technique can keep the image not strict and keep the precision of observations. For comparison, we also calculate the result of other follow-up observations for the same asteroid, and there is no significant upward trend, but the uncertainty here is bigger than our RDS observations. So we think RDS technique can keep the precision of measurement for faint objects and can achieve better accuracy than the average level of follow-up observations. This is the accuracy we got. It's about 0.24 in rate accession and 0.032 arcsecond in declination. We also investigate the ability of observing fast-moving asteroids, and the strict images were cause trouble for positional measurement. It will increase the error in the direction of motion. So here we depict the relationship between the long track, cross track residuals with the rate of motion. On the right figure, for the other follow-up observations, there is a significant upward trend in AT residuals. This is likely because the strict image or timing error. But for the RDS observations, the AT residuals is almost flat, and RDS technique can also work well for the fast-moving asteroid. For near-Earth asteroid, whose rate of motion exceeds 10 degrees per day, the root mean square of residuals is 0.35 in 80 directions and 0.23 arcsecond in 30 directions. For newly discovered asteroid, we calculate the changes of standard deviation of observation residuals with magnitude and rate of motion for one apparition near Earth asteroid. This is changes with magnitude, and the red figure is changes with rate of motions. Here, the red circle expresses the asteroid without well-determined orbit before the observations, and the blue ones are the others, the rest. So we can't see the significant different trend in these figures. So we think RDS technique can achieve good precision for newly discovered asteroids which do not have accurate ephemeris. We also do some experiment to investigate where the error comes from. The main errors is likely due to the instability of telescope, which we use the special RDS astrometric reduction that we use 3 different CCD frames to determine the orbit of asteroid. These figures give the possible pointing deviation of the Lishan telescope. It's about 0.2 arcsecond on average. Okay, the conclusion part, the RDS technique conduct precision position measurement of asteroids when they pass by the Earth with small aperture telescope, and we give the RDS observation accuracy, and this technique work well for observing fast asteroid, faint object, and also newly discovered asteroid. If you're interested in our work, you can find more details in our article published in AGA this year. And thank you for your attention.
Thank you for the presentation. Unfortunately, we don't have any time for question. If anyone have a question, you can discuss personally. And yeah, and this is the end of the today's section. Thanks again to our speaker for on this session and our attendee. Thank you. Have a nice day. Night.
Just some announcements. So tomorrow we don't have any sessions. Our next session is only on Thursday. The first session is a poster session at 10 in the morning. It's only a single poster, and that's the poster by Colin. So I just remind you that that won't be in the regular poster hall. It will be here in this venue. So it will be a half-an-hour poster slash discussion session with Colin. Thank you.
Thank you.
The photo.
Can I have another one of the book? Thanks so much, sir.
That's part of the room.
Properly. Tomorrow, if this thing doesn't work, don't call my name, eh?
And you see that's why this morning the charger didn't want to charge.
I told you, don't put your WhatsApp here, you don't listen. What if they call you? Hey, almost there. Look, there are 3 messages there. Mama sent a message.
Not safe, Papa.
Ah!
Of doing this.
Do you know what this machine is doing? It's doing Zoom and it's streaming.
And you putting
And the WhatsApp is here.
Almost there.
WhatsApp. Message is being copied.
That's why they're chasing us out of this country, because we're looking for trouble, us. Where there's no trouble. You see now that Nigerian lady, they say, although you were born here, you must go. Why is those stuff stuck here, Papa? Anyway, this machine needed